Welcome to this lecture about the course outline. Section 1 is where we're at, talking about the course itself. Section 2 is where the action actually starts. So there we will learn the definition of data engineering and also useful tips for what the data engineer should know. Then we will jump into section 3, in which we will introduce you to the data engineering ecosystem. Here we will learn computer science concepts, we will talk about the cloud and its services, and we will talk about data. We will talk a lot about data. In section 4, we will clarify what are data sources and destinations, and we will talk also about data pipelines, and we will talk a lot about data pipelines because this is a crucial area of data engineering. Also, we will interact with an API using Python. In section 5, we will focus on data modeling. So from what exactly is data modeling, how can we do that in a data warehouse, and how can we do that in a data lake? In section 6, we will focus on data wrangling. Okay, so we will cover data cleaning, data transformations, and data validation using both SQL and Python. Finally, in section 7, we will talk about Airflow and how can we orchestrate multiple data pipelines. As you can see, there's a lot of ground to cover, so let's jump into the real action. Thank you, and I will see you in the next video. Welcome to the second section of this course, which is actually the first one about data engineering itself, even that the first one was about the course introduction. So in this section 2, I will present you one definition of data engineering, and please note that there might be others you can find elsewhere, and in this analytics area it's somehow difficult to clearly define the boundaries between the roles. There are a lot of different roles and some functions might overlap those of the others, but this will be an acceptable one. So I will also try to explain you what a data engineer typically does. And next, we will jump into some of the skills and tools that a good data engineer must have. So thank you, and I will see you in the next video. Welcome to this lecture. So data engineering is a very broad area which can somehow be summarized in very simple terms. And that's what makes this area so unique and special. Essentially, there's only one thing that matters in data engineering. You must bring data from one place to the other. Looks simple, right? Yes and no. So you have to do that, which looks simple, but you will have to make sure that you don't lose data along the way, and that the process is done on an efficient way. In the middle of that, you'll have to interact with a very wide variety of tools and at the same time understand the business needs so that you don't break anything in the process, and also always provide the data that was actually requested from you. That's why I think this area is more of a craft, and that's also why I'm presenting you this definition. So data engineering is the craft of bringing data from one place to the other as efficiently as possible without compromising data integrity and data quality. We will look deeper into all of these little steps and details of this definition in the next section, so stay tuned and focused. Data engineering is also part of this data analytics ecosystem, which is composed of many roles and activities, all of those around data. From all of those roles, I would say that data engineering is the most needed for companies. Not because we're special, or even, I'm not saying that without a data engineer, a modern company can't survive, but without it, there's no structured approach to business intelligence and, well, data reports, dashboards, which are always crucial nowadays, can also be built, but if they're not structured in an efficient way, things will get difficult. Also, one thing that is very noticeable recently, or in the past few years, is that from the time that data science and machine learning buzzwords started to show up, it quickly became clear that most companies weren't exactly ready for such advanced interaction with data technologies. So data engineering became more relevant. And that's Also why this is a very high demanding area, which is good for you and also probably part of the reason why you're here. But don't get way too excited. I won't lie to you. This is a very demanding and challenging area. There are a lot of new tools always showing up, and plus, depending on the company you will work for, this can be somehow stressful as well. If you're responsible for real-time ingestion of important business data and something breaks, you'll need to fix it ASAP. Also, don't be scared. It's a very pleasant and good area to work at, and you'll be exposed to a lot of problems and learnings that will enrich your career for sure. So stay tuned, stay focused, learn the most you can, and thank you. I'll see you in the next lecture. Welcome to this lesson. We've talked a little about data engineering, so the definition of a data engineer should now be a little easier. I will present you with some terms I haven't defined just yet, but don't worry, you will hear them frequently, and in future sections they will become clearer and clearer. So here it is. A data engineer builds, maintains, and manages data pipelines to ensure that the flow of data from the operational world to the analytical one occurs in the desired seamless manner. Again, things like pipelines, operational versus analytical worlds will become clearer, but for now, just know that the ultimate goal of data engineering is to bring data from one place to the other and to make it useful for the business. That means that you will have to extract it from somewhere, and this somewhere resides on the typical operations of the company. And load it elsewhere where it will be useful for analytical purposes. And for that, a set of transformations must occur so that business can actually extract information from all the data that you just move. Given all of this, here's a list of things that a data engineer should do. So a data engineer should master data engineering essential tools, be knowledgeable of software engineering principles. So you won't be a software engineer, but you'll need some principles. You'll need to code some things. So also understand data analysis, data science, machine learning needs. So as long as you at least know what these roles or functions do, it will be very useful for you. Also, you'll need to be business savvy. So you need to know the business you're at, and you'll need to know the needs of the business. Also, you'll need to distinguish between storage and processing and memory. We will talk about all of these computer science basic concepts. You'll need to be acquainted to version control and CI/CD, so you will do code and you will have to do PRs, you'll have to handle all of that as well. And essentially be ready to continuously learn. But hey, that's why you're already here, to learn. So congrats, that important step is already within your reach. Now I'm going to give you 3 examples of typical requests that might be requested to you as a data engineer. So imagine that operations reach you out. They want to build a new dashboard. What do you need to do as a data engineer? So you'll need to understand their needs. And this part is essentially one of the most difficult ones. So people don't often talk the same language in different departments of the company that you work for. So make some effort to really understand their needs. Meet with them if needed. It will be useful and it will be better. Also look for the needed data. So once you know what the needs are, you'll have to look for the data. And then you'll have to bring it to the final destination. And of course, you'll have to model after the needs that you were requested to. And then finally, just deliver the results and iterate over them. It's typically very common for the final result not to be achieved at the first iteration. Another example. So CEO wants some typical metrics, but now in real time. So you have a dashboard, there's a couple of metrics, and now the CEO needs those metrics to be on his hand faster. So you need to understand the current architecture of the implemented solution. You'll have to design the strategy to implement a new one. You'll have to study which solution best fits your needs. You have to build the pipelines and again, iterate over the results. And in this case, you'll have to compare the results with the previous ones. Another example. So finance wants to slash your data warehouse costs. So your data warehouse is too expensive. And now you'll need to look for unneeded tables and schemas. You'll need to optimize data pipelines orchestration to make sure that everything is handled and especially processing is handled in a very efficient manner. And you have to better use distribution keys or add other database optimization tools. As you can see throughout these examples, there are common things. You will interact with a lot of people, sometimes people who are not experts in data, but are experts in their own field. You'll face a very wide variety of requests, all of them, of course, around data, and you will have to dominate and be able to work with a lot of data-related tools. Sounds exciting, so let's dig a little deeper into these skills and tools that you might need. Thank you, and I will see you in the next lesson. Welcome to this lecture on the essential skills and tools that a data engineer should have. Data engineering is the closest analytics role to software engineering, so don't be surprised to see some skills related to software here as well. And starting exactly with one of those, so programming skills. SQL and Python are the most common programming languages that we use, but Scala or even Java are equally important for big data handling. Then the second most important skill is data modeling. Without that, you won't be able to pick the right transformations to apply to your data. Of course, that technologies related to data storage are equally important to know, so SQL and NoSQL are kind of a must. I've mentioned data modeling, which is kind of a strategic goal when dealing with data. Here I'm focusing more on the actual data wrangling process. So you'll need to know how to bring what you need from a dataset, and that is achieved through transformations. We'll talk a lot about them, and we will also practice them. Version control is gradually becoming more and more relevant as the analytics area becomes more and more entangled with software engineering. So be also familiar with version control. And of course, cloud. So it's becoming less and less frequent for companies to own their own infrastructure. So knowing about cloud service is definitely a plus. Of course, that the rest of general purposes of engineering also apply. So know the business you're working at and know how to solve problems. Great. Now, some more detail in terms of the tools that you'll certainly be exposed to. So data warehouses and data lakes are very common. You need a place to store your data. Either Redshift, Snowflake, BigQuery, or S3, those will be part of your daily activities. We also saw that transformations are crucial in data engineering. So of course, you'll need some tools that can make your life easier. So that there are a lot of ETL tools that can help you here. So Fivetran, Talent, Medallion, AWS Glue, etc. Those are all tools that can be very useful for you. Then how fast will you apply your transformations? If this needs to be fast, things like Kafka, Kinesis, or PubSubs are tools that will be of use for you. Of course, that you'll probably be also exposed to a lot of data, so Spark can also show up to help you there. And like I said in the beginning, you'll be exposed to a lot of data pipelines that will need to be orchestrated. So expect to use tools like Airflow, AWS Step Functions, or Google Cloud Composer. Finally, the ultimate goal of the transformations you'll apply is to be able to get information out of data. So apart from making sure that bad data quality doesn't affect your conclusions, visualization tools will be part of your daily life, or at least you'll be feeding them. Here, Looker, Tableau, or Power BI can be of help. So as you can see, there are a lot of things that you'll need to be acquainted to be successful in data engineering. I hope this course helps you in setting the basis for you to thrive in this amazing field. So thank you, and I'll see you in the next
Welcome
lecture.
to this lesson. We're just summing up the section so far. So we've covered essentially the data engineering definition, and we saw exactly what is supposed to for a data engineer to do, and exactly what kind of tools, skills one must have to be a successful data engineer. So there are a lot of things that you'll need to do in terms of the tools that you'll use. There are a variety of tools that will be used throughout this data engineering ecosystem, but just focus on some of them for you to know more about just a few number of ones. It will be useful for your data engineering job, and then of course that you'll need to keep on learning more new tools. They are constantly being updated, or there are constantly new tools showing up. So you'll need to have this mindset of constantly upgrading your knowledge and experimenting with new tools. And sometimes these new tools will have they will be very new, so there will be it will be difficult for you to get to know the details about them, learn them. But yeah, just focus that you'll need to have this mindset of learning and learning and learning and experimenting a lot. And of course, the skills we've went through the main skills that a data engineer should have. It's very important for you to be very technical, but it's also very important for you to get to know the business in which you're working at. So there will be business definitions that will probably shape the way that you will model your data, or affect the way that you'll just trigger or schedule some data pipelines. We will of course know more about it in the next few sections, but this is essentially what we covered out on this introduction, on this section that is still very introductory. So I hope you enjoyed this section, and we'll see you in our next one. Thank you.
Welcome to section 3. So after introducing you to the course and then to data engineering, let's take a walk through its ecosystem. This is a vast one, I'm not going to lie here, and in this section I'll not only talk about the basic concepts, but also dig deeper into cloud services and data. Hope you enjoy, and that by the end of this section you have learned why companies tend to choose a cloud environment for their data operations, what are the main differences between the operational world and the analytical one, and that you are able to enumerate data types, the characteristics of big data, and also some of the most important data formats. So thank you, and I'll see you in the next lesson. Welcome to this section outline. So now that you know what are the learning objectives for this third part of the course, let's see how we're going to cover that. So we'll start with the basics. There will be a brief introduction about computers, from what's a CPU to RAM and storage, and this part will help you understand the building blocks of cloud operations. Then, before moving to the cloud, let's dive into why companies tend to move their operations to the cloud. And next, the cloud and its services. This part will be very useful for you to understand what kinds of services can be used to deal with data at scale. And then in the fourth part, data. That's an important one. After all, it's the first word in the job. So here we'll talk about structured and unstructured data, data formats, size of data, and also data types. And finally, we'll end this section with the differences between the operations world and the analytics one. And of course, you may expect some quizzes here and there. So thank you, and I'll see you in the next lecture. Welcome to this lesson. Let's now learn a little about the basics of computers. This is especially important to clearly distinguish the needs when working with data. Storing data is different from processing it, and there's multiple ways for processing it. Also, somewhere you'll have to move data around. So all of these operations are done by a different part of a computer. So let's talk about the basics. Computer is a set of components put together so that we can perform operations. The computer has a motherboard, which is responsible for connecting and kind of orchestrating things between the different components. This board is the base of everything, putting things together. So it allows connectivity to peripherals like screens and other devices, as well as external connectivity to computer networks. Also, the CPU is the brain of the computer, so it's responsible for processing and executing instructions. It stands for Central Processing Unit, and it's responsible for processing and executing instructions, like I said, such as data aggregations or other transformations. It can have more than one core, which means that it can handle parallel tasks, and also it's typically measured in hertz or its multiples. Then there's the RAM, which is a storage type whose purpose is to maintain data available for short-term operations. It stands for Random Access Memory, and it is used for temporarily stored data that is used in active processes. So you can think of it as a place to store intermediary calculation steps, which are then aggregated by the CPU on a later stage. This data is volatile, which means that it is cleared on shutdown and is typically also measured in bytes or its multiples. Then we have the hard drive. It's the central unit for storage. It stores data permanently, which means that data stays after the computer is shut down. So it's typically meant for long-term usage, although there are some advancements or needs in which it is also used as an auxiliary storage for active processes. Disks can be magnetic, HDD, which stands for hard disk drives, or a flash memory type, which is SSD, stands for solid state disk, and also this is typically measured in bytes and in its multiples. Then we have the GPU, which is responsible for processing graphics, but they are useful in other ways. It stands for Graphics Processing Unit, and it's a dedicated type of processor for rendering graphics, although it has recently been leveraged for other types of processing, namely for data-related tasks, since it handles parallel processing in a very efficient manner. And then there's the connectivity. So there are a lot of components for connectivity, and this basically allows a computer to be connected to the internet or other computers. Computer networks are hierarchical and cost efficient since they exist so that we don't need to connect all computers to all computers. There are several types of networks, either local or non-local, like the internet. Each computer has its own address, which is the IP address, a unique identifier on the network, and it is also able to send small units of data to other computers, and these small units are called data packets. Network-specific devices like routers or switches will then direct the data packets to the right destinations, typically to other computers. So you can think of computer networks as basically the mail network. So you can send a postcard from your address to another person's address, and the mail network will do that for you, as long as you follow a set of rules and codes, of course. So in the case of computer networks, the rules are a set of protocols that must be followed, like the TCP/IP, the HTTP or HTTPS, and also the domain name system. This basically works like a mailing network that will deliver data packets instead of a postcard. So now that you are a little more familiar with the basics of computers, let's jump into the next video, which is about the cloud. So thanks, and I'll see you in the next video. Welcome to this lesson. I have referred the cloud several times already. It is an important element for every modern company, both for data and software. But there's an alternative. Actually, it was the first alternative that showed up. So in this video, we will take a look into both environments. First, on-prem, which is short for on-premises. It refers to a setup in which a company owns all the IT infrastructure it needs to operate. In other words, it means that the company will have its own set of servers and computers and handles their maintenance and upgrades. The cloud, which is the alternative, refers to computer services which are provided over the internet by a third party. This essentially means that there's another company that kind of rents its IT infrastructure or servers for other companies to operate. So the main difference between these two environments resides exactly on who owns, maintains, and upgrades the servers, processing units, storage units, etc. for each company to operate. Within these two options, the cloud is often and increasingly the preferred solution. And let's see why that happens. So the cloud is cost efficient. Think about it. Your company would have to buy a lot of computer hardware, install it somewhere safe, maintain it, and often buy additional hardware. This would be extremely expensive. Besides, the cloud is also scalable. Imagine that your company has a lot of sales and it's facing a severe peak during Christmas time. It would have to quickly buy more hardware and install it before the season ends, or face business loss because the web store stopped working. The cloud solves this easily because you can always rent more computer power on the fly from your provider. Then it's also more accessible. You can quickly and easily start using cloud services over the internet. Speed to market is also much faster on the cloud. Imagine starting a company and before writing the code for the website and starting to run it, you would have to buy servers, rent a basement somewhere. It's doable, but it takes longer to get to your customers. And finally, the focus. With cloud services, your company doesn't have to manage any infrastructure at all, which means that it can focus on its own business. So these are the reasons why cloud services are nowadays the go-to solution. Of course, that they are tailored in many ways, which means that companies can choose between different levels of managing them. But let's talk about it next. So thank you, and I'll see you in the next video. Welcome to this lesson. Now that you are familiar with the basics of computers and why the cloud gained a lot of traction, let's explore some of the cloud services you'll probably use or be exposed to as a data engineer. Starting with storage. You need to store your data somewhere. It will either be a database or a file storage service. These provide disk space and are typically known as data lakes. You can think of them as your local folder repository where you store media files, CSV files, or text files. Some examples of storage cloud services are AWS S3, Google Cloud Storage, or Azure Data Lake Storage. These services have become cheaper and cheaper throughout the years, and that helped a lot companies scale their operations. So summing up, when you use these services, you are essentially renting up disk space over the internet to store your files instead of buying hard disk drives to add to your servers. Next, let's talk about compute. Here we refer to data processing capabilities. We refer more to CPU, but also to memory-intensive operations. Compute services vary widely across cloud providers, and there's often a lot of options with different details that you can adapt and tailor to your needs. These services include virtual machines, containers, and serverless options. Some examples are AWS Lambda or EC2, Google Compute Engine or Kubernetes Engine, and also Azure Functions. In all of these, remember, what you're actually doing is renting CPUs over the internet to do operations on your data instead of buying and installing them on your own infrastructure. The big advantage here is availability and also scalability, which is often essential in data processing. Now let's talk about the other big storage solution. You can store your data in files, but you can also store it in databases. On the cloud, you can find database solutions for your operations and also for your analytic needs, both for structured and unstructured data. And here are a few examples. So AWS RDS, Redshift, DynamoDB, BigQuery, or Azure SQL database. And now, network services. These are related to ways to optimize and distribute resources. For example, content distribution network, load balancers, DNS, and VPN. The first will help companies better distribute their content, like Netflix, which needs to quickly deliver video, it probably will want that content to be geographically close to its users and use a CDN for that. Load balancer helps dealing with website traffic distribution, for example. DNS helps improve site reliability, and VPN establishes secure private access to network resources. Before we finish, just remember these few things. Cloud services will help you a lot with your data problems, but they are not only for data problem solving. Also, as a data engineer, you need to know the basics of each, and as there's a lot of cloud service providers and services, just focus on a few of them, the ones you need to perform your tasks. I hope you enjoyed this video. Thanks, and I'll see you in the next video. Welcome to this lesson. So we've been so far talking a lot about the second word in the data engineering job. So now let's focus on the first one. We've seen some computer engineering concepts and also talked about the cloud, but now it's time to know a little more about data. So we'll now start a series of lessons about it. And there's nothing better than actually starting defining it for a start. So what is data? What comes to your mind? Data can be defined as an elementary description of an event, activity, transaction, or more broadly, thing that is recorded, categorized, and stored. This is, of course, one definition, and it's not set in stone, but typically data is actually this: one row recorded on a table on a database to describe one event, for instance, a purchase, or a set of characteristics about a person recorded on a text file and stored on a hard disk drive. Data refers to something elementary, and once you're able to organize it either on a database or in a folder or in a file, it becomes information. With information, you can have knowledge. So from a single transaction's data, you organize it and group it with other transactions, and you'll be able to know if you're selling more or less than, let's say, last year. This is the power of data, and it's becoming more and more obvious the need for this type of knowledge to provide business value. Thank you, and I'll see you in the next lesson. Welcome to this lesson. After a definition of data, let's focus on a structure. From the previous examples, we can deduce some conclusions on what is structure. So on the first one, there was a row on a table on a database that described the transaction. In this case, there's probably one column with the value of that transaction and another one with the date. This means that every transaction would have to have these fields that describe that transaction, meaning that we have some structure, a clear organization on how data is stored. On the second example, we had a text file with a description of a person. Now, we can have two options. We either describe the person like this using some predefined traits, in which we would have data with a certain structure but not a fixed one, or a second option where we would have more freedom to describe each person. That's also data, but it's what we call unstructured data, in the sense that there's not a very clear structure to it. We either can describe one person with 10 characters or with 1 million. So let's now dig into the differences between these three types of data structure, which are structured data, semi-structured data, and unstructured data. The borders between the late two are somehow blurred, but between them and the first, they are very clear. Structured data is highly organized with fixed fields. Like in our example before, a transaction is always described by 3 characteristics, and those fields in that case are a data type, a time type, and a currency type, clearly defined at the start. In that example, we used the database table, but a CSV or TSV file would also be fine. We will talk about data formats later, don't worry. Semi-structured data can be a JSON or other markup type format file. It can also be a NoSQL database, but what is certain is that there's a structure to this data, but not totally set in stone. We saw a set of fields that describe a person, but someone could add another one to describe a distinctive trait of one particular person, or the size of the fields would be flexible. On the other end, text files image files, emails, etc., they can be categorized as unstructured data. These are typically files you can load into a data lake, and that can vary in schema and be text-heavy or media-related files. So, to sum up, data describes an event, transaction, or thing, and you can do it on structured, semi-structured, and unstructured way. So hope you enjoyed this lesson, and I'll see you in the next video. Welcome to this lesson. Let's now talk about data types. Now that you know about data structure, you understand that data has sometimes a lot of fields to describe a transaction, an event, or a thing. But are all those fields the same? The answer is no. Sometimes a number describes a particular field, other times it's a set of words or even a date. So that's why data types are important to distinguish all those fields describing data, and also to, in the case of structured data, for some restrictions, since you don't want a date field to be filled with just a character. So here are the main data types. Integers and floats are for numbers, either integers or with a decimal point. These have then some subtypes, but let's not focus on them here. Characters and strings are for single characters or multiple characters. Depending on the size accepted, you can have a whole book as a string, for example. Boolean is for true and false fields, while date and time are for time-related features. There are then some more complex ones like lists, tuples, or dictionaries, which are more of data structures instead of types. Also, there are many other custom types you can be exposed to, like currencies, binary fields, etc. These are just the most common ones. So thank you, and I'll see you in the next video. Welcome to this lesson. We've went so far through data structure, which is kind of an external characteristics of data. Data type, which relates to every particular piece of data. And now let's focus on where data is. Specifically, let's focus on the cases in which our data is stored in files. All files have a format, and formats have specificities. We'll walk through the most common ones in the context of data, and the first format we will discuss is the text-based format. In this case, the data is stored in a text file, which can have data fields separated by commas, in the case of CSV, or comma-separated values, or by tabs, which are tab-separated values files. There are other varieties of text files which are similar to these two, but mostly differ according to the character that separates the data fields or columns. Another text-based file is the JSON file, which stands for JavaScript Object Notation. It's a widely used format, and it consists of dictionaries nested inside other dictionaries. It is a very flexible type of file, and you can add virtually any data type on each field. Then we have the XML file, which stands for Extensible Markup Language. It also has a tree-like structure, and its tags have to open and close around the data you're storing there. Another file format, which has been picking up some speed recently, is the YAML file format. It stands for YAML Ain't Markup Language, and it's very easy to read, and it's based on indents and dashes. As you can see, it's a very human-friendly format. This one ends the text-based format files I'm presenting you. All of these are widely used, some more than others, but they have one thing in common: text, which means that if you want to store them, you'll need a data lake. But we'll cover that on a future lesson. For now, let's jump into the binary-based formats. These kind of files are all about compression and optimization. I'm briefly covering some of them, like 4 types, which are the most important ones, but they all have this feature in common. They are typically used in setups in which speed or the size of data are a relevant constraint. Starting with Avro. These are row-based formats in which an entry is on a row, meaning that each row of these files represent the characteristics of one transaction or one event or one thing. They include the definition of the schema along with the data, and they are typically used in streaming and messaging schemes. Now let's talk about another binary file format, Parquet. Contrary to Avro, this one stores each event, transaction, or thing's characteristic in a column instead of a row. Although this might seem a strange way to organize data, it is a very efficient one and widely used in analytics. For example, AWS Redshift stores data the same way as a Parquet file, a very similar one, at least in principle. These files and Avro ones are also very good with data serialization and deserialization. The first is the process of transforming complex data structures into standard formats that allow them to be stored and transmitted to be deserialized later. Kind of an encryption, but without the secret part and with a focus on efficiency. Another file format is protobuf, which was developed by Google and heavily used in microservices and real-time applications. Finally, we have the ORC file format, which stands for Optimized Row Columnar. Like Parquet, these type of files are also store data by columns instead of by rows. This one was developed for Apache Hive at first, and it's also very well optimized for analytical queries. Now for another very different and common file format, media formats. Images are usually in JPEG, PNG, or GIF. Audio typically stored in MP3, WAV, or AAC, and video is in MP4, AVI, or MKV. I mentioned data lakes in the first part on the text-based formats, but all of these file formats have the same in common. If you want to store them, you'll either need a file system, or if you use the cloud, you'll store them on a data lake or on a lakehouse. We'll cover that on the next section of this course, but for now, I hope you enjoyed this lesson and that you're now more familiarized with file formats. So thank you, and I'll see you in the next video. Welcome to this lesson. Let's now talk about big data. You've heard that already, and often possibly it's a so-called buzzword, but there's a lot of things behind this buzz. Big data is real and a very big challenge for a data engineer. We'll briefly talk about ways to handle this challenge later in the course, but first let's focus on the definition of big data. Here we often hear about the V's, which are a set of words starting with V that help us with that definition. Starting with the first, volume. So when we talk about big data, we essentially talk about a lot of data. Gigabytes, terabytes, or petabytes of data. Millions, hundreds of millions, or billions of records of transactions or files. But big data is not only about volume. The second V is velocity. You can even have less amount of data than a terabyte, but it can arrive very fast to your platform. Another V is variety of everything, either data sources, data structure, or even the granularity of data. You can receive data with different granularity, which stands by what a row of your data represents. It can be an order or the items bought inside that order. These three Vs for a certain time were kind of enough to describe big data, but then they were expanded to help with the definition. Variability in the schemas was added, veracity with the data was also added, viscosity to define which data is kept and requires some action, for example, to be cleaned, and value to refer to data that becomes valuable for the company to be used. So now that you know a little more about big data, let's hope that you enjoyed the lesson, and I'll see you in the next video. Welcome to this lesson. We have discussed the engineering side of data engineering, and on the previous set of videos we have learned a few more concepts related to data. Now let's talk about the environment a data engineer and more broadly an analytics professional works at, the so-called analytical world. There are two worlds on a company, the one in which the company operates and the one in which the company makes business decisions and studies the business. Let's call the first one the operational world and the second one the analytical world. These two differ in a lot of things. One of those is the purpose. While the first focus on day-to-day activities, the other one serves the purpose of supporting business decisions. In terms of data volume, the first one handles small data increases, transaction by transaction, inserted into an operational database as the sales occur. The second one deals with large data sets, such as all the sales of the previous day. This is part of the reason why the first one has to be ACID compliant, while the second one doesn't. We'll talk about this on a short while. Some examples on different databases are MySQL, Postgres, or Oracle in the operational world, and BigQuery, Snowflake, or Redshift on the analytical world. Talking more about those databases, the operational ones are more suited to short and simple CRUD transactions, while the analytical ones are tailored to allow complex analytical queries. The operational world is based on or focused on the day-to-day activities, which means that its database operations are write heavy, constantly including new transactions at a high pace. The analytical world leads more with heavy read operations to drag data sets from data for analysis periodically. I referred ACID compliance. Let's now focus on that. This stands for atomicity, consistency, isolation, and durability. The first concept can be better explained with a money transfer example. If you transfer $100 from account A to account B and the credit operation on the account B fails, then the old transaction must fail. This makes sense because otherwise client A would have less $100 that had basically vanished. So atomicity stands for a transaction is all or nothing. Consistency means that all the constraints on a database are respected by all data in it. If a business rule tells you that an account can't be negative, then the last transaction that turns its value negative shall not be accepted. Isolation refers to handle transactions independently. If client A transfers money to client B, and then this client B transfers money to client C, these are two transactions, not just one from client A to client C. Durability is all about preserving the data. Changes on a database are permanent. These set of rules need to be applied to the operations world, but they can be a little more relaxed on the analytical one, since the focus there is on studying data. So summing up, the operational world is the world where things happen and records of data are created to support business regular day-to-day tasks, while the analytical world is a world of thoughts, of analysis, where we abstract from the day-to-day activities of a company and focus on studying and finding patterns in the data that comes from the daily operations to look for further efficiency gains and other insights that allow the business to grow. So I hope you enjoyed this lesson and concepts, and I'll see you in the next video. Welcome to this video. So in this section, we have covered a lot of new concepts, and now that you are more familiarized with them, you'll be able to better understand the environment a data engineer typically works at. We've covered the basics of computers, from what processes data to where should we store the results of it, to the cloud, which is basically one computer rented over the internet. We've discussed a lot of different concepts related to data, and we ended up the session understanding the differences between what operations are in a company and why data or analytics is typically separated and requires more abstract way of operating. So I hope you enjoyed this section, and I'll see you in the next one. Welcome to section 4, and congrats on reaching this part of the course so far. Up until now, we mostly focused on the basics and introductory concepts to start building the knowledge to become a successful data engineer. Now let's focus on the knowledge itself. In this section, we will talk about the main concepts of data engineering, which typically reside around one activity, moving data from one side to the other. So by the end of this section, you will be able to know what it means to bring data from one side to the other, enumerate which of these sides typically are, and of course, know what to do in the process. This is an extensive section, but stay focused because you'll learn a lot of new and important concepts. Thank you, and I will see you in the next video. Welcome to this lesson. Let's now see what we will talk about in this section 4 called From Data Sources to Destinations. We will begin with data sources and focus on what are these data sources, at least the more common ones. Next, we will talk about the destinations or data repositories. After that, the data movement. We will discuss what are data pipelines. And finally, we will look into the velocity of data in those data pipelines and talk about the difference between batch and real-time. I hope you enjoyed this section and that you take the most out of it. I believe it's an important section and that the concepts we will discuss will help you a lot on your data engineering journey. Thank you, and I will see you in the next video. Welcome to this lesson. Let's start this section with data sources, which are a set of places, let's call it that way, where data is before you grab it to move it somewhere else. These data sources are typically on the so-called operational world, and they are constantly being updated as part of the day-to-day business activities. There are a lot of different types of data sources. We will cover a lot of them in detail, the most common ones, I would say, and we will just share some features of the others. Operational databases are the main source of data, usually, either transactions or products or client details. Normally, these just reside on a few tables of an operational database. Your job as a data engineer will be to bring that and transform it into actionable data from where business decision makers will be able to take conclusions. We will talk also about that process later. APIs are also trending and relevant source of data these days, such as files, whose main formats we have already covered extensively in the previous section. Then you may also have to deal with streaming data coming or not from sensors and IoT devices. In addition, logs and other monitoring systems are also sources of data, and you can be exposed to them depending on the maturity and nature of your organization. These are the main data sources, and we will dig deeper into them on the next few lessons. So thank you, and I'll see you on the next video. Welcome to this lecture. Let's talk about operational databases. These are databases designed to handle operational data, which is typically in the form of small data inputs or additions to existing data. They handle these at high speed. So we're talking about write-heavy operations. For these, as they are where company operations rely on, integrity, security, and reliability are essential. Also, these need to be ACID compliant. And finally, as a definition, these databases store all the business processes around someone buying something. To interact with these databases, either structured SQL or NoSQL are the standard, with the first being the most used one. Here are some examples, but don't worry too much if you don't understand them now or they are not that clear, but we will learn more about SQL in the section 6 of this course. Thank you, and I will see you in the next lesson. Welcome to this lesson. Let's now talk about another very common data source, the API. API stands for Application Programming Interface, and it's a process that enables software to talk to software. The communication is based on a set of rules and definition that allow information sharing from the server to the client. The most common used APIs are REST APIs, which define a set of functions that can be called by the client. Here, the communication occurs via HTTP and the response is in plain data. In general terms, this is what happens when you interact with an API. There's a database somewhere, and there's this interface for it that is accessible by the client application. There's a set of endpoints and a set of rules, and your application can make an HTTP request to call the API, which then gathers data from databases and for example, returns a list of cars. Okay. In other example, another call is made, but this time the method is different, and the goal is to retrieve the list of most popular items, most popular cars of the week. So essentially, an API stands between a database or several and the client, and it allows for a computer program to interact with it as long as a set of established rules are respected. All of these HTTP calls that I referred in the previous slide have some common methods. The get method is used to retrieve data. The post method is used to create a new entry on a database. For example, we discussed in the previous examples that you can use an API to get data, but you can also use them to insert data into a database. The put method updates an existing resource, and the delete method deletes a resource from a database. So now that you know all of these details, you might be asking, how do we actually interact with an API? You need to create a request which has a list of rules for every API. There's a request line which defines what are you doing and where, meaning what method are you using and what endpoint is your target. The API headers contain metadata about your API call, like the authorization, the content type, and other details. The query parameters define filters. For example, you may be requesting a list of products from an API, but only wanting products that of a certain type. The path parameters are similar, and they identify special resources, and the request body as the data payload, and then there's also the authentication part if that's not included in the header. Focusing now on the authentication part, it's easy to understand that sometimes the person who develops the API doesn't want everyone to access it. It makes sense since data must be protected even inside the same company. So every time you call an API, you might need to handle the authentication part. There are several options here, and the first one is the API key, which is a secret to access it and is sent on the request header. Another option is the bearer token, which is kind of a more secure option. You log in some system, grant access permission to your application, and then a token is generated for you. You'll then use that token to include in the bearer, and that way your application will have access to the API. Finally, a more simplistic way is the user and password method, which is less secure but always better than just an open access API, which can also be an option depending on the data that you're sharing. So we have covered APIs, the structure of the request, and also a little about authentication. But how do we write the request? Well, there's options for many languages. Here's one for HTTP. Another one in Bash, and yet another one in Python. We will work on an example of a Python API code in which we will use something very similar to this, so don't worry to spend more time here. So now what's missing on this data source is the response pattern, because sometimes it can go wrong, right? So there are a couple of response types. The 100 response types are related to informational responses. These are codes that indicate that the request was received and the process is continued. These are not very used in practical terms. The 200 codes are the ones where we are always looking for. They indicate success. The 300s response codes indicate redirection, which tells that maybe more action is needed by the client. The 400s indicates client errors. When these occur, you'll need to modify the request, fix it, and send it again. The 500 codes indicate server errors and tell you that the server failed to fulfill the valid request. From all these codes, here's a list of the most common used. So the 200 okay, the 400 bad request, which tells you that the server didn't understand the request due to some invalid syntax. The 401 unauthorized, that says that you don't have access to the resource. The 404 tells you that the server can't find the resource. And finally, the 500, which tells you that the server encountered an unexpected condition and can't fulfill your request. So it was a lot, but I think that a good summary of this important data source. APIs are widely used nowadays, and you now know that they can make the bridge between the application you developed and the database with the data you need. Or that you need to update. In order to do so, your application needs to be written, or at least the part that handles the API call, in code that allows you to address it correctly. It can either be in HTTP, Python, Shell, etc. That address has a set of rules, from the method to the endpoint to the request header and the authentication. All of that you'll need to take care of. And even then, you might have the wrong response from the API, either because there's a mistake on your side or on the server side. But ideally, all things will go well and you'll be able to get the data from this very common data source. I know this was an extensive lesson, but it's a useful one for your job as a data engineer. Thank you, and I'll see you in the next lesson. Welcome to this lesson. Continuing on our journey about data sources, let's now discuss one we have already kind of covered: files. We talked about files, formats, so now let's just say that sometimes data comes from files, which are either directly loaded into repositories or that are loaded from data lakes or from local disks. These files can also come from file transfer protocols like FTO, FTP, SFTP, or FTPS, which are protocols that exist to transfer files over a network. Next, streaming data. These kind of sources are becoming more and more common, and they are part of real-time or near real-time setups. They usually arrive at high speed and lead to kind of complex systems. Finally, logs and monitoring systems are often data sources for semi-structured data. So they require knowledge about the monitor systems, and you can either be exposed to them or not, depending on the maturity of your company. So now that we covered a lot of data sources, let's focus next on data destinations or data repositories. Thank you, and I'll see you in the next lesson.
Welcome to this lecture, which is actually an exercise. So the first coding exercise that we will have in this course. In this one, particularly, we will be fetching data from an API. So we will get some data about earthquakes. We will use this URL, we will explore it in a bit, and the goal will be to use a query to query the API and to get data between January 2024 and the 1st of June 2024. We will want a list of earthquakes with a minimum magnitude of 5.0, and we want the response to be in this GeoJSON format. The output, the expected output of this coding exercise will be CSV file with an ID, type, time, title, magnitude, place, if the earthquake was felt or not, if there was an alert, and then the longitude and latitude of the place where the earthquake occurred. As part of the solution, we will first begin to explore the website. Then we will create a virtual environment, install some libraries, both JSON, pandas, and requests, then build the code and print the final result, or see the output also as the CSV, which was the goal. In this particular exercise, there are two options. You can build a virtual environment and run Python code, but we will, in the solution, we will choose to do everything inside a Python, a Jupyter notebook. So it means that the virtual environment is already created. We just need to actually import the libraries that are needed. Then you build the code and you'll be able to print the results of each cell. But we will also have the option to create a virtual environment and run Python inside that virtual environment. So let's now jump into the API, or at least the API documentation. So in a lot of these exercises, and you will have a lot of pipelines which start with fetching data from an API. You'll see that probably 80 to 90% of your time around these types of exercises or types of pipelines, you'll be spending that time reading through documentation. So here you can see that this is from the USGS service. It has earthquakes from all over the world, and they make this data about earthquakes available for anyone. So there's no authentication needed for this type of service, although in a regular API which has like private data or so, you'll be probably requested to implement authentication. Not in this case. So here you can see some documentation about this. There's a JSON format. I think that the request will be to get in a format called GeoJSON. Then we will use a query. So this is a query that was made, or this is an example by the people who maintain this documentation. But basically, there's the URL, so you can see that the endpoint will be here if you want to submit a query, which is basically this URL that we're going to use as a base URL to call the API. And then after the question mark, you can see that there are parameters that we will pass to the requests library in Python that will help us actually make the API call. You can see that this format is the format that was on the exercise. So the response will come in GeoJSON. You can find a start time and an end time, but there are actually more parameters that you can include. You can see here again the format. If you use this format, if you press here, you'll see that the response will have this kind of structure. So it's a JSON, but it has more tweaks to it. You can see that there's an initial part with metadata about the response itself, and then actually the features or the earthquakes, which will be the earthquakes for which the parameters or filters that you apply will be respected. So basically, if you want a magnitude higher than 5.0, that means that if around that time, so the start time was January 2024 and the end time June 2024. So if in that time there are earthquakes with a magnitude bigger than 5.0, this means that your response will be a list of those earthquakes. These are the columns, like say, that you will export then into a CSV, and here you can see that there's a geometry part which has the longitude, the latitude that you will also need. So now let's jump into Jupyter Notebook. So basically, this is was already initiated. This is part of Anaconda ecosystem. So you can install Anaconda on your computer, and then you can run Jupyter Notebooks. And basically, this is already set up to Python T. But for example, if we start to import one library that we will use, you can just press run, or you can just shift enter, and it will run. Every time that the cell is running, there's an asterisk here. Once it runs, it will clear or print the result. In this case, this cell ran in first place. We will also import another library that we will use, which is the request library. So you can see that it ran in second place. And now let's build our call. So first we will handle the API call itself. So we will need to have a base URL, which I'm going to copy from the website. So if I come back here, I'll just copy this URL, which is the one I'll be using for this exercise. So this is our base URL. So it's a variable that we're going to be using. And now we want the parameters which are in the exercise. So let's go to here and find out yeah, so basically we want data between January 2024 and the beginning of June 2024, the magnitude and the format will be here. So basically, let's build those parameters. So this is GeoJSON. Then we will have start date or start time, which is 2024 January 1st. Then the same thing for the end time till June, and then we'll have a mean magnitude of 5. Okay, so these are our parameters that we will use on the call. So, and for now we're just going to make that call. So we're getting data from there, so we will use the get method, and we are going to call this particular endpoint of the API, which is the one that will reply to our queries, and we don't need to use any authentication because this is a public API with public data. And we are just going to pass these parameters. So we will get the format in GeoJSON, minimum magnitude is 5, and then the dates between January 2024 and June 2024. So basically, if I run this means that my code is now querying the API, and I can print the response status code to see if it was successful. So if you remember, this 200 response code means that it was actually a success. So it means that we are actually having a response somewhere. So if I go response.json and I print it, then basically you can see that this is very similar to this format. So we will have some initial fields in this response that we don't actually need for this exercise, and then we'll have a list of features or a list of earthquakes. And you can see that the first was in Kermadec Islands in New Zealand with 5.2 magnitude, which actually respects the minimum magnitude of 5.0. You can see that there are then more features to it. You can see that there are coordinates, so this would be longitude and latitude. If we go back here, we see that the coordinates have longitude, latitude, and depth. So for now, depth is out of reach for this exercise. So now it's time for us to actually build the rest of our code. So it's typically a good solution or to include some sort of check. So only if the status code is 200, you continue with your code. Else, if not, then probably you'll just print that you'll have some sort of error. Error fetching. Okay. Fetching data on the API. You can just print these if there's an error. So for example, I'll just do these. And I'll rerun everything. You can see that the status code. Okay, this is. Okay, so this is a different status code. So if I run this cell, the output will be that there was a. Okay, so there was an error, actually, an error calling the API. So basically that's exactly where you're going to want to have some logic checks on the response codes. So now we don't want to print success. We actually want our logic to be implemented here. So what we will want is a CSV file. So we will use pandas library to help us. So we will begin to actually build a list of earthquakes, which is the response.json, and then we will want just the features. So this will, if I go here, I'm just basically requesting these this list. So it's a list of all of the earthquakes that respect our conditions, and basically I'll then create the pandas data frame. For now, it's empty. So I'll build just this data frame. And I'll just build with the final columns that we will need. So it's the, so here, the ID, the type, the time, title, magnitude. So type, title, magnitude, and then place, fields, alert, and longitude, latitude. Place, fields, alerts, longitude, and latitude. Okay, so this data frame is empty at the beginning. So the goal for us will be to just have a for cycle that will go through all of these earthquakes. So this is a list of earthquakes. So remember that I'm just requesting these entries. So the list of earthquakes, and inside each earthquake there are two data dictionaries, the properties one, which I'm going to grab magnitude, place, time, etc., and another data dictionary, which is a geometry, from which I'll grab the coordinates, and then the first two elements of this list, which is called coordinates, are the ones that I'm going to be requested, so longitude and latitude. So now that I've built, let's do just a quick sanity check to see if everything is fine. So I'll need to do this, print response code. Okay, and now if I go and print, so it's printing all the earthquakes on this list. So now there's no error. So we should be fine here. Okay, so now let's get the actual data out of the response. So I'm inside this list of earthquakes. So for each element, I'll need to get actually the data that I want. So I'll grab the ID. ID will be here, and then I'll grab the rest. So it will be the type. Type is inside properties, and then I want the type. Okay, so if I go here, type should be somewhere. Yeah, type is here. It's a string. It's inside the data dictionary properties. And if I go here, you can see that I grabbed the ID from the root. So basically, inside each earthquake, there's this field, which is the type, and then there's this ID, and then this geometry, and these properties data dictionary, and we want to grab different things from different places. So type is from here, title, I think I'm missing something. Type time, okay, type title doesn't have this. Time, title, okay, so it's time, and now I'll copy these to title. Now should be magnitude, place, alert, Longitude and latitude will be similar, but from geometry. Okay. So it will be longitude. Copy from here. And coordinate. And now this is a list, so I want 0, which is the first element on the coordinates list, is the latitude, longitude, I think. Yeah, longitude and then latitude. Okay, so 0, 1. Now it's time, title, mag, place, felt, and it's missing one, alerts. Alert. Okay. I think we should be fine. So this is one information for the earthquake, and now I can actually build a pandas data frame on top of this. Sorry. So I'm going to pass this data dictionary that I built. So this is going to generate a data frame which is called df earthquake, and then I want to append these to actually the final result. So it will be df and df earthquake. These would be appended. So every time that we go through the for cycle inside the list of earthquakes, it will generate actually the earthquake, and then we'll keep on adding to the end of the data frame. So basically, this data frame is empty in the beginning. So on the first iteration, will just be this df earthquake data frame will be added to an empty one, and then it will keep on going through the for cycle. And then after I quit the for cycle, what I want to do is actually it's actually to export in CSV. Let me run this. It's generating just a warning, so it's some feature that's going to be out of place. And let's go and check the folder to see that actually it built the solution. So I'll just open this CSV. Probably just open with the text editor. And once it opens, I can also check here. So if I refresh, see that, yeah, this earthquake CSV was created a few seconds ago. So it was created by my notebook. It's probably going to be open somewhere. Yeah, so here it is. So this is actually the response code. So you see that the first earthquake was in New Zealand, so here it is in the CSV format. So it means that we were successful on the call to the API and also on the transformation. So this is a kind of exercise that will happen a lot, and you see that we spent a few time, not that much, but we spent some time through reading through the API documentation to explore it a bit. There's more down here, so we use end time, start time. We also used the maximum magnitude or minimum magnitude parameter. So there are a lot of things here on the documentation. Typically, we'll lose a lot of time. Well, we spend a lot of time going through API documentation, and then we build the code, which is relatively simple. So it's just the part of the data transformation is what usually takes more time, but this one was quite simple. So we're just fetching an API and then printing a CSV file as a result. But sometimes you'll have some other data repository or some other file format that you will use. But essentially, this is the kind of API call exercises that you will face as a data engineer. So I hope that you enjoyed this lesson, which was actually an exercise. So thank you, and I'll see you on the next one.
Welcome to this lesson. Now it's time to know where we typically put data after ingesting it from a data source. In a few videos, we will also talk about the process in between, but now let's focus on destinations for data. These data repositories exist in the analytical world, and they have to be adapted to the speed at which data arrives, which can be distinguished between real or near real-time and batch. Of course, there are several data repositories available. Data warehouses are the most common ones, but data lakes and lakehouses are also common nowadays. Data marts are usually included in data warehouses and alternatively to the so-called normal databases. There are also the NoSQL databases. Interestingly enough, some data sources can also be data repositories, as in the end of your work as a data engineering on a data engineering pipeline, you may need to download data in a specific file format or send it somewhere like to an FTP or an API which loads data into an external databases. On the next few videos, we will detail these data repositories, so stay tuned, and I hope that you enjoy the next few videos. Thank you, and I'll see you in the next one. Welcome to this lesson. Let's now talk about the most common and most important data repositories: data warehouses, data lakes, and lakehouses. Starting with the data warehouses. These are the cornerstone of analytics. They are designed to have high performance on running analytical queries, which tend to have a lot of aggregations, joins, and complex structures. Data warehouses handle only structured data, so data that can be stored on a table with defined and well-known fields. To do this at scale, some data warehouses can be based on columnar storage, storing data by column instead of by row. These data repositories are thus primarily built for business intelligence and reporting. Some examples are AWS Redshift, BigQuery, and Snowflake. Data lakes are fundamentally different from data warehouses. They are designed to store large volumes of data in raw files. They support both structured, semi-structured, and unstructured data, and are typically used to support machine learning tasks. Some examples are AWS S3, Google Cloud Storage, and Azure Data Lakes Storage. Finally, data lakehouses are relatively new, and they combine the benefits of data lakes and data warehouses, allowing for both BI and ML to be on the same platform. Here, Databricks, Delta Lake, or Google Big Lake are some examples. In terms of comparisons and focusing on what I haven't covered yet, data warehouses are optimized for SQL and their schema is on write, meaning that the structure must be well defined at the start. As for the data lakes, they can store video and other media files and tend to store a lot of data. Their schema is typically on read, as the focus is to store data that will then be used later. As you can see, there's a lot of flexibility for you to choose the right repository for data. So next, let's focus on some additional data repositories that you might come across on your data engineering journey. Thank you, and I'll see you in the next lesson. Welcome to this lesson. As typically a subset of a data warehouse, data marts are data repositories which have a few tables for specific analysis. Mostly they are department-specific. They are for department-specific reports and only have relevant data for a specific business area. These are useful when the finance department, for example, wants some analysis which require a set of tables that handles operational data in a way that only makes sense from a finance perspective. You can have multiple data marts stored on your data warehouse or none at all, depending on the needs. Next, let's dive deeper into another type of data repository. So thank you, and I'll see you in the next lesson. Welcome to this lesson. After covering most of the most common data repositories, let's now talk about one which is also a database, but relies on an entirely different and recent approach to store data. we'll talk about NoSQL databases. These are databases for unstructured data, and that's why they are called NoSQL databases. NoSQL stands for the contrary of SQL, which means structured query language, indicating that it's a programming language that can operate on structured data. These databases are known for offering flexibility of data modeling. Also, they are highly scalable and support high-speed data processing. And also, they have high availability with replication and fault tolerance. All these characteristics make we think, why don't we use these databases more often? But be assured that some of these characteristics also apply to data warehouses, and that NoSQL databases are suitable for specific needs that sometimes require this or that specificity, but generally all needs have in common one thing: data is unstructured. There are a few types of NoSQL databases. Let's now focus on some of them, starting with the document databases. In these, data is typically stored in JSON, and one example is MongoDB. They are generally good for content management and e-commerce catalogs. Another type of NoSQL databases are key value stores. Here, values can be of any data format, and these solutions are extremely scalable and useful for real-time data ingestion or building user profiles, like supporting recommender systems. Some examples are Redis or AWS DynamoDB. Another type is the wide column stores like Cassandra or HBase. Here, that is stored in columns rather than in rows, and they are very efficient with sparse data and have a high throughput. They are typically good with IoT, log data, and analytics on time series. Finally, the graph databases, for which data is stored in nodes and edges, and highly optimized for queries on graphs. Social networks and fraud detection are good examples, and Neo4j or AWS Neptune are examples of these databases. So we covered another data repository that you may find when working as a data engineer, so let's now jump into the last one for this section. Thank you, and I'll see you in the next. Welcome to this lesson. We have talked about these types of data repositories in the data sources section, but don't be alarmed, this is perfectly normal. So sometimes API is a source of data, or some other times you can also write data into one. Same happens with files and protocol file transfer protocols. There will be for sure cases in which you'll use them in various ways. This is the last video on the data repository, so I hope that by now you'll have more familiarity with all of these concepts that we talked about in the previous videos. So let's now jump into data pipelines. So thank you, and I'll see you in the next lesson. Welcome to this lesson. We have talked about data sources and data repositories, so now let's focus on one of the most recurrent and important tasks a data engineer has: building data pipelines. Before that, let's define what a data pipeline is. A data pipeline is a set of computational processes that allow data to be brought from one place to the other, meaning that it is a set of instructions that are executed in order to bring data from the source to its destination or repository. And what do we mean by a set of computational processes? Well, they are mainly related to simple executions that allow us to extract data, transform data, and load data. These instructions can generally be done in two orders, which define very well the differences between two types of data pipelines. Let's start with the first one, the ETL. In this type of data pipeline, we'll bring data from the source to the destination, but in the middle, there is a set of transformations that need to be done. So the pipeline first handles the data extraction, then loads it into this staging area, which is a non-mandatory intermediate layer that exists. Then data transformations occur, and the pipeline finally loads data into the destination in its final format. This is exactly why these data pipelines are called ETL, because they extract, transform, and load data in this order. The alternative is the ELT approach, and this is a most recent trend in which data also travels from source to destination, but the pipeline extracts the data and loads it, and then the transformation will occur as the data is needed to be processed in other business activities. The first type is mostly used in legacy business intelligence, and it's typically executed in batch. It's mostly reliable and it reduces the workload on the data warehouse because data is loaded in a structured and analytical ready way. On the other hand, the ELT type of data pipelines is more suited for real-time and modern data analytics processes. It scales easily because the data transformations are done after, which means that the heavy work will be done at query time or when the rest of the process continues. Here are some examples of tools that are suited to help you build ETL pipelines. AWS Glue is one example, as well as Azure Data Factory and Google Data Flow. As for ELT, dbt and Snowflake are two examples that can be involved, although most of these tools, if applied correctly, can help you build any data pipeline. So summing up, data pipelines bring data from one place to the other, and they can either extract, transform, and load data into the destination, or extract, load it, and then reserve the transformations for someone in the future activities. I hope you enjoyed this lesson. Thank you, and I'll see you in the next video. Welcome to this lesson. We briefly referred batch and real-time or near real-time. This is a difference on data pipelines across a specific metric or characteristic, which is speed. Data pipelines can differ in the speed or periodicity they run, meaning the number of times per a time period in which they bring data from the source to the data repository. Let's start with batch processing. This is the traditional approach to analytics. The data is collected, processed, and loaded by the pipeline in batches or groups of data. The typical example is the pipeline that runs all night and that brings data from the previous day into the analytical world. These pipelines are easy to build, and as they run periodically, although they tend to perform heavy computational processes, they can be cost efficient. These pipelines does have high latency and can run for several hours, and their goal is to provide historical analysis. Some examples of tools that can be associated with these are Hadoop, AWS Glue, or Snowflake, but really any data warehouse can take the computational effort on them. A really different approach is the real-time data pipeline. These processes data continuously and as it is produced, so it's more or less like they are constantly running, if not completely, at least constantly checking if there's new data that needs to be ingested and loaded into the destination. That's why they are typically referred as event-driven. They will be triggered sometimes when an event occurs. They are harder to implement and tend to be more expensive, a lot more expensive in some situations. They are more suited for live monitoring or instant analytics. That's why their latency is relatively low. Some examples are Kafka, Flink, or AWS Kinesis. Also, these pipelines can differ in their approach to real-time data ingestion. One of these types are the brokers. Brokers are a middleware component on a larger setup. They are responsible for managing the communication between the entity that produces the data and the entity that consumes the data. They can temporarily store matches for consumers, and they typically handle load balancing by themselves. Another type of real-time data pipeline are the pub/sub ones. Here, publishers send a message to a topic to which subscribers listen to. Subscribers are the data consumption applications which receive the messages that are broadcasted to these topics. The message can then be persistent or no in the broker, and there can be a one-to-many or many-to-many relations. Examples of these are Google PubSub, Kafka Topics, and AWS SNS. Finally, The other type of real-time data pipelines are message queues. Here, producers send a message to a queue, and consumers pull messages from the queue. The communication is handled one-to-one, since each message is delivered to one consumer only. Messages are usually removed once the consumer consumes them. Examples of these are RabbitMQ or AWS SQS. An alternative to these two main data pipelines approaches when it comes to speed of data ingestion is the Lambda architecture. In these, we have kind of take an hybrid approach. There are 3 layers. One that occurs in batch, another in real time or near real time, and the third one that combines the output from both. An example here would be like a weather app with real time and historical weather info. Here is an example of the setup. So we have the batch layer, the speed layer, then the servicing layer. Here are the 2 types of batch and real-time data pipelines approach, and then the query could be done to the servicing layer, the speed layer, which would combine different types of data arriving at different speeds. So we covered a lot in simple terms about data pipelines that can differ on their speed, so on how fast they are executed and how fast they ingest data. There are 2 types essentially here. So the batch, which is a more traditional approach, and the real-time or more modern approach, which is tailored for instant analytics or monitoring applications. On the second ones, there are many options to apply real-time analytics, and you can choose from brokers, message queues, or pub/sub approaches, depending on which option is better for your needs. And of course, you can always have an hybrid approach to your environment, which is exactly what the Lambda architecture allows you to. So thank you, and I'll see you in the next lesson. Welcome to this section, Sum Up, in which we cover the essential concepts around one of the most important tasks a data engineer has, which is bringing data from one place to the other. We've learned about data sources, meaning the place where data typically is, data repositories, which is the place where we typically load data into, and data pipelines, which is what connects them. So a set of computational processes that allows us to bring data from data sources to repositories. Regarding data pipelines, we saw 2 differences across different aspects. One of them was where in the data pipeline the transformations on our data occur. There we have 2 options. Either they occur in the middle, before loading into the data repository, and thus we would have a traditional ETL data pipeline, or they occur after we load the data into the repository, meaning that we would have a more modern approach to the data pipeline, which is an ELT data pipeline. Also, the other difference that we saw was among the speed of data inside the data pipeline. If this is done with high latency, then it's a batch pipeline. If not, it's a real-time pipeline, and we understand that these serve different purposes. So I hope that you enjoyed this section. I hope that you understood these concepts very clearly, and let's now jump into the next section. Thank you, and I'll see you in the next video. Welcome to section 5, and of course, congrats on reaching so far. You're now turning into an expert in data engineering. After learning about the job and its details, about the environment in which a data engineer typically works, and about data on the previous section, you focused on learning about data sources, data repositories, and data pipelines. Now it's time to learn about the essential part of the work of a data engineer: data modeling. This is the part in which you, as a data engineer, will learn that what sorts of transformations make sense for you to apply to your data so that it is delivered or loaded into its final destination as a almost perfect piece of consolidated, structured, and organized information ready for analysis. This means that in this section, you'll learn techniques that will help you know what transformations you should do and how to start the process of studying them before starting to build your data pipeline. Hope that you take the most out of this section and that by the end of it you are more familiarized with concepts like star schema, medallion model, and how you can build your own data model. Thank you, and I'll see you in the next video. Welcome to this video. As mentioned before, this section is all about data modeling. So we will start with what is data modeling. I'll present you a definition and detail one of the most important tasks of a data engineer. Then let's talk about star schemas. This is a widely used data modeling approach, and in this part of this section, I'll detail dimension and fact tables and show you some examples. After that, I'll briefly discuss another option, the snowflake schema, and then yet another one, the data vault. Finally, and before building a data model from scratch, which is something that we will also be doing in this section, let's talk about an ELT approach to deal with data modeling, the medallion model. Then the building of a data model from scratch, like I said, and finally, in the end of this section, there will be tips on how to optimize your BI solution. This is again an extensive section and one of the most important ones in this whole course. So go through it slowly and carefully. Listen to the videos more than once if you need, and then try to apply these concepts. So I hope you enjoy this, and let's have fun modeling data. Thank you, and I'll see you in the next lesson. Welcome to the first lesson of section 5. Here, let's finally discuss about data modeling. So what is, after all, data modeling? One definition can say that data modeling is the process of designing the structure and the organization of data so that it stays in a format and shape which allows for effective reporting, analysis, and decision-making process. In other words, modeling data is keeping it tidy and ready for the needs that business units have for it. As we've gone through them, data can be used in many ways in a business environment, so it's good that it is available on an organized way so that it can be used as fast as possible. So this process is needed for optimizing all of the analytical needs that a process originates within a company related to data. Typically, these come from the need of totals or aggregations, like the total number of orders in the previous week or in the current week, or a comparison between the two, or even orders by store, for example. So we need to make sure that data is kept in a user-friendly way and designed for analysts to quickly pick it up. Next, we will dig deeper into one of the main organizational schemas for data, and that leaves it ready for analysis and similar purpose. So thank you, and I'll see you in the next video. Welcome to this lesson. Now is the right time to talk about one of the most common, versatile, and easy to set up data modeling options, the star schema. This schema is a dimensional model approach to events that occur and that have characteristics that are often integrated into their analysis. The star schema is a schema in which we model these business events around a small set of tables resembling a star. It has one central table, which is the fact or event table, and then several dimension tables connected to this central table. This schema has heavily normalized data. And normalization in a database is a design principle aimed at reducing redundancy and improving data integrity by organizing data in multiple tables. One way of understanding normalization is with an example of an order from a particular customer. Can you imagine storing the customer name, address, birth date, and other details along with every single order? In this case, data is not stored in one table, but rather split into several tables which are related to each other on logical groupings. Okay, now back to the star schema. Event granularity is what defines a row on the central table. You can track an order by order, or you can track product by product sales, or you can track daily orders, for example. So granularity is up to you and depends on the goals of your project. Data modeling is just a way for you to make sure that your data helps you and the business reach analytical goals. So defining granularity and the components of fact and dimension tables are always up to you and need to be as aligned as possible with the business needs. Here's an example of a star schema with one central table called the sales fact. This one is a fact table, and we will see more details on what a fact table is on the next lesson. And then there are several other tables that connect to this central one. In this example, you don't see it as resembling a star, but the truth is that if you move the central table to a central position, you'll understand why this data modeling option is called a star schema. So now let's move on to the details on these two types of tables, the fact and the dimension ones. So thank you, and I'll see you in the next lesson. Welcome to this video. Let's now talk more about the central fact table within a star schema. It is the fact table, a long table in which every row is an event you're going to analyze. They have typically this structure, so they are long, they have a lot of rows, which mean that there are a lot of business events that they are tracking, and just a handful of columns. And apart from metrics like totals of an order or like some other groupings, these tables only store foreign keys that allow you to make connections to the other tables in the star schema, meaning there's a few columns dedicated to event metrics, a lot of rows, and few other columns which are related to foreign keys, which allow you to connect these central table to the other tables in the star schema, meaning the dimension tables. And typically there's only one fact table by business scope. We'll see a few examples in a while, but essentially one example is one row of sale with the total number of items, the total spent on that sale, and then other foreign keys to the customer table, another one to the product table, which allows you to join to these other dimensional tables. So fact tables are all about a lot of transactions stored in rows with the granularity you decided, and keys that allow you to connect these fact tables to other tables, which we will describe in the next video. But before that, let's now talk about types of fact tables. There are several, and they widely solve most of your analytical needs. There are transactional tables, which are the most common ones. There are periodic fact tables, and there are accumulating fact tables. Let's now see some examples of these. Transactional fact tables record individual events. One sale, one click, one transaction, one transfer, etc. They'll have a few metrics like the ones you see here, and then a few foreign keys. In this example, you can see two metrics: the sales amount, which is an aggregation of the value of each item in that sale, and the total number of items on that sale. As you can see, to get these metrics, you'll have to create a pipeline from an operational database and perform a series of transformations to calculate these aggregated metrics. So basically an ETL, right? You're now successfully connecting the dots. Let's quickly sum that up. So you have a need, which is to analyze sales, and you have applied a data modeling technique that allows you to build this transactional fact table. And then you actually build a data pipeline to extract data from the source in the operational world and load it into a data warehouse with the aggregated metrics, leaving all the business need for the analysis. Someone will then build a dashboard, a report, or just make a business decision. And congrats, you're a successful data engineer. That's what you've been studying for. So now continuing to other parts of the knowledge you need. So periodic fact tables are fact tables which capture aggregated data at regular intervals. So sales by the day, by the month, by the quarter, etc. Okay, so they group metrics around some period. Finally, the accumulating fact tables which track the life cycle of an event or process. with rows updated as the process makes progress. These are specially designed for processes that have several steps, like the 1 year. So someone orders something on a particular date, then someone on your company prepares the order, then the order is shipped, and then the order is delivered. So this is a case in which probably if you're into logistics, you'll be handling a lot of these kind of accumulating fact tables. You track the process of an event in your business. So about fact tables, it's all. Let's now check the other kinds of tables on a star schema that allow you to describe the events you're tracking with your own fact table. So these other tables are called the dimension tables. So thank you, and I'll see you in the next video. Welcome to this lesson. Now that we've seen what a star schema is and the main different options for fact tables, let's focus on the dimension tables. Dimension tables are all about the context of the facts you're storing on your fact table. These tables contain a primary key plus a list of attributes for each dimension. For example, it can be a product table, and the attributes here would be the primary key and then the characteristics of the products, like the type of product, the product category, product size, etc. These tables then often are very wide and smaller than fact tables, which kind of makes sense. So a product can have 100 characteristics from the size of the color, type, etc., type of package, etc. But it's not expected for your company to have millions and millions of products. So this is already, this is another of the main differences between dimension and fact tables. Dimension tables tend to be wide, while facts are narrow with a small amount of columns. And then dimension don't have a lot of a big number of rows when compared to fact tables, which tend to can track like millions and millions of sales. Now, on the primary key side, on a dimension table, they are typically called natural keys, meaning that the identifier of a unique row often comes directly from the operational world, like a product SKU, for instance. It's often a good practice to change that unique key to something else, because these keys might be subjected to changes in the operational world, and also they don't offer any business logic. Here enter the so-called surrogate keys, which are primary keys of a simpler form, usually integers and sequential. These primary keys decouple the analytical world from the operational one, and they simplify the joins. Plus, by creating them on your ETL pipeline, you'll be able to kind of enforce one row, one key, and thus avoid duplicates. This is important because often data warehouses can't enforce uniqueness on keys. So remember when we said that ACID compliance could be softer on the analytical part? Yeah, analytical world is more relaxed in terms of the demands for strictness, from the operational world. Another important characteristics of dimension tables, and that also distinguish them from the fact tables, is the fact that these change slowly. So in fact, they are often referred to as slowly changing dimensions, in the sense that the characteristics or context of a sale or another event don't often change. However, events are always occurring. Let's see an example. So imagine that a product table, you have a product table with the attributes of the product, so your website sells. It's not expecting for your products to change daily. This means that someday a new product is added, and that's when you add a new row to your table. The same with the client address on the customer dimension table. People are not always changing their addresses, like they're not changing their address every week, for example. So these dimension tables tend to be static and not changing frequently. However, when a change occurs, you'll need to make sure you have a strategy to deal with that, because on the other hand, sales occur all the time, and this might affect your analysis and your businesses. So imagine that you're tracking sales for customers on one city. If all of your customers, or a significant portion of them, moves away from that city, that may impact your business analysis. So that's why it's important to know all the types of dimension tables that exist. We've seen before types of fact tables. Now we see types of dimension tables. So type 0 dimension tables exist, and they are often called as fixed value. Type 1s, they override. Type 2, they add a new row, and type 3, they add a new column. This is a summary of their characteristics, but let's dig deeper into each one of these. So starting with type 0, fixed value. So this slowly changing dimension is called fixed value for a reason. So you have a customer, you fill that data into the customer table once he becomes a customer, and that's it. So from an analytics point of view, you don't care about that anymore. So it's not important for your business, but only if it's not important for your business. I'm not saying that this is always the case. So you just need to know, for example, that the number of clients you have, and you don't care about where they were born or where they live. So from a business point of view, in this case, you're saying that this doesn't matter. Even if there's a typo somewhere in your table. So this doesn't matter. So customer ID C001 will always be customer name, and you joined at that date, and this will never change. It's kind of set in stone. So this is a type 0 slowly changing dimension. Or maybe you care about that. So you often offer discounts on every customer's birthday, for example. So you need to update the error that was made. This means that you want to track any updates to the fields on the customer table, which means that you will be using a type 1 slowly changing dimension, in which any change will override the past values. So in this example, for example, imagine that John Doe changes from New York to San Francisco. That means that on that date, on the date he changed, or that you know that he changed the city and his address, you'll update that row belonging to John Doe. Okay, this means that a new city will show up in the address city, and the effective date is also updated. Type 2 slowly changing dimensions are all about keeping track of history. So, for example, an important customer, John Doe, changed to another city. You want to run your analysis of sales city by city, but if you use the previous type of slowly changing dimensions, all of the sales of John Doe will be moving with him from one city to the other. But that's not correct, right? So type 2 slowly changing dimensions help you track the changes by creating a new row when the attribute whose change you want to track changes. So in this case, he moved away from New York. That means that it's not its current city anymore, and you just add a new row with the address of that new city and the effective date when the change occurred, and that's the current entry for John Doe. Type 3 slowly changing dimension is similar, but you add a column instead of a row pointing to the previous value. So it had a similar effect, and it's more useful if you only care about the latest value before the change and the change you're tracking, and not exactly all of the changes. So imagine that you're only tracking address changes and not like the rest of or city changes instead of street changes, for example. So summing up, there are a few different types of dimension tables, of slowly changing dimension tables, and the strategy to pick one over the other depends on what you need for your analysis. Their main difference resides on when something changes, whether you want to store those changes history or not. And you can have also kind of multiple types under the same table. So if you treat attributes from certain columns differently from the others, and this kind of makes sense because you might be interested in keep tracking of the previous address, but not his weight, for example. So thank you, and I'll see you in the next lesson.
Welcome to this lesson. In this case, we are going to go through one example. So the first example about star schemas. In this particular case, we're going to watch or take a closer look at the orders. So we have let's say a business, and there's orders as customers that make some orders, and orders contain products, which can be one or more product in the same order. And we will want to track these using a star schema. So in the end, there will be probably a dashboard that will track the orders or sales, whatever you want to call. And in this case, the granularity of our main table will be the order. So there will be one line per order. So in this case, here is the star schema. So you can see that there's a central fact table which track events, and the events in this case are the orders. That was what I was explaining before. So basically there will be one line per order. So you can, if you will take a look at the shape of this table, you'll see that it's a relatively, it's not that large, but it looks like it's going to be big. So this means that you'll probably just track a few metrics according to these orders, but you'll hopefully have a lot of orders in your business. So it means that it will be a long table. So it basically will have few columns, a few number of columns, and a lot of rows, or at least that's what is expected out of your business. And then you can see that there are 4-dimension tables. It can be more, it can be less, but typically 4 is the right number to go. And you can see that here we are tracking customer details, store details, order details, and also time details, let's say. So in these 4 tables, which are dimensions, we will have the characteristics of the ecosystem around the order, which will help us make conclusions like what kind of customers make orders, when do they make orders, which are the traits of the order themselves, and where do they make the order. So these tables are built generally by those questions that you ask about your own business and the fact or events that you want to track in your business. So in this case, and typically what happens is these dimension tables tend to have a lot of columns because you tend to have a lot of characteristics for each one of them, and you'll have just a few number of lines. Of course that you want to have a lot of customers, but it's typically you'll have more orders than customers. So this will have more rows than this. And also for the stores, so you'll have just a few stores maybe. Even if you have a lot of stores, it's typically normal for a business to have more orders than stores. So let's now take a look at the tables themselves. So you saw that there's a shape resembling a star, so that's why it's called star schema. But let's now focus on the details. So here you can see that there are, and I'm going to zoom in a little bit. So you can see that the fact order will have order ID, store ID, customer ID, and date time. So date time can be actually a key that connects to the dimension of time, dimension table of time. So these are 4 foreign keys that you can use to connect to the dimensions. And then apart from the keys, you'll have just 2 metrics in this case. So one order can have more than one item. So we're tracking the number of items per order and also the value of the order. So how much did the customer pay for the products inside this order. So each one of these keys connects to the dimension tables that you see here. So for example, these, and remember, dimension tables will help you provide context about the event that you're tracking. So it's important to see exactly where the store is located, if the store is a big store or a small store, if there's which are the opening hours, can be also relevant for the type of analysis that you'll do. For the orders, we can have type of order, if it's for delivery or not, what kind of payment are the customers using, and then let's go here to the customers themselves. So we can have a table with the city, the nationality, the country, or the address where the customer resides. Some of these trades can have null, so you can have or no or don't have all the data about these customers. So just pick the right dimensions or pick the right trades that you want to to be tracking in these dimension tables. And then this time dimension, which is kind of optional more and more, specifically because data warehouses and all of these dashboard BI tools tend to have a lot of functions that can help you already track these time-related traits, let's say. But if you want to build, it's okay, but it's kind of hard to maintain because of well, entries like is holiday. So if it is a holiday, it can depend on the year, it can depend on the country that your customers are in. So these type of dimensions are difficult to maintain, but you can for sure build a table just to track every day or every timestamp, and that's the second reason why these dimension tables related to time tend to be less and less used, because they can get very big and cause problems, performance problems on your problem. So on your exercise. So imagine that you want to track orders. So orders have a timestamp. That means that it goes to the second, for example. So that would mean that you would have one entry per second year. That's a lot of entries for a dimension table. So yeah, just be mindful on what kind of things you want to track, and yeah, just be mindful of trying to avoid performance issues. So yeah, this is our first star schema. It's a typical star schema. You can have also slight variants of these one, but typically you'll find these dimensions as useful, and throughout your problems and exercises that as a data engineer, you'll come up with very similar dimensions and fact tables. So I hope you enjoyed this lesson, and I'll see you on the next one.
Welcome to this video. Now that you learn one of the most common and important data modeling approaches, let's learn about another one, the snowflake schema, which is totally not affiliated with the cloud data warehouse called Snowflake. So this one is somehow similar, however, similar to the star schema. However, dimension tables are normalized. If you remember, normalization is all about reducing redundancy, meaning that you organize your data in a way that nothing is repeated and is split across multiple tables. The snowflake schema takes these a step further by splitting the dimension tables into several ones. That makes the star schema transforming visually into a snowflake. So this approach reduces space because you have more tables, but they have less redundancy. For example, on a star schema, you may have a slowly changing dimension type 2 with a customer address. Whereas on a snowflake schema approach, you would have one customer table which would be connected to a city table, and this one to a country table, thus effectively avoiding to repeat city names on the customer table. So here you see two customers in the same city and two cities in the same country, which would turn into something like this. This is a set of three smaller tables which are connected through foreign keys. So instead of just one dimension table, it transforms into three, which are kind of hierarchical by geography in this case. As a comparison between the two types of schemas, Snowflake schema works well if you want detailed dimensions and often allows you to perform richer analysis. However, there are of course some downsides. One of them is the costlier joins. For a simple analysis on a customer sale by city, you'll need to at least do two join operations: fact table to customer, customer to table to city table. Also, there's a need for you to keep good track of all the tables and all the ways they are related, which is more difficult at scale. So now that you know one more data modeling technique, let's now jump into yet another one. The data vault option is a more recent one and not yet widely used, but it's important for you to know the most common examples. So thank you, and I'll see you in the next lesson.
Welcome to this lesson. In this lesson, we were going to go through a second example of data modeling, and we will look at the first snowflake schema that you'll face throughout this course. So the snowflake schema is as we've seen, slightly different from star schema, but the basis under which we get to that model is very similar. The only difference is snowflake schema, tables, and data is normalized. So it means that we will have more tables. That's why we move from a star schema or a star shape to a snowflake shape, in which the dimension tables will have kind of ramifications into other tables. So let's go back to the example that we saw for the star schema. So if you remember correctly, so we have one fact order. We are tracking orders. Orders can have more than one item, and orders are ordered by someone. They are ordered somewhere at a specific time, and they have some details that allows us to have a context of those orders. So, for example, how is that order paid? This is a star schema, but on a snowflake schema approach, we can see things like city and country being placed in one specific table or two. For example, it can be more. And this means that essentially we will only write a city name once instead of constantly repeating cities in this table. So this means that data is more normalized, which also means that we will have more joins in the end, but this guarantees us that every time that we need to update one city for, I don't know, change of name or change of number of inhabitants or whatever, we just do that operation once, which means that data integrity is easier to keep. So if I scroll to the right, we'll see exactly the same schema. And you can imagine that if I zoom out, you'll see just one dimension here or another table for another dimension that is connected to the customer dimension. But if you imagine more tables like these around these other dimensions, you'll see that the resemblance will be more of a snowflake shape. So that's why the name. So in this case, we just replace the location of the customer instead of keeping a record in every entry for every customer of city name and country name. We just created one new table, which is the location ID, or it can be like dim customer location, and we have its ID. That's the value that we will going to be keeping on the customer dimension. And then here you'll see city and country. So imagine that if you have only 5 cities and 100 customers, so instead of repeating 5 cities over and over and over again on 100 rows in this table, you'll just repeat it 5 times. So this table will have 5 entries, which are the 5 cities, and this one will be keeping 100 entries for those 100 customers. Each one of them will have the 5 keys, one of the 5 keys to connect to this location. So this is our snowflake schema. I just expanded one of the dimensions, but every time that you want to apply a snowflake schema to get data more normalized, just make sure that you keep on going through a hierarchy of entries. For example, here I named it location and dim location, but it can be dim country, and then again another one here which will have the city inside each country. So this exercise can be made in several ways. I hope you enjoyed it. It was probably your first snowflake schema. Snowflake schemas are not that common, or at least typically star schemas are more applied, but this can also be one solution for your data modeling problems. So thank you, and I hope you enjoyed the lesson, and I'll see you on the next video.
Welcome to this lesson. The Data Vault approach to data modeling offers more flexibility and scalability, although is less frequently used. It's useful especially when you have a lot of changes in business rules. Here the key concepts are hubs, links, and satellites. Let's now see more details on those. So this data modeling option focuses on hubs, which are core business entities like customer, product, or order. Although some business rules may change, you will always have these entities interacting. So these are hubs for your analysis. Then you have links between these entities, which are in a form of a table with surrogate keys. For example, a sale is an interaction between two ups, customer and order. Finally, there are satellites, which add descriptions to the hubs and the links, kind of what dimension tables are for star schemas, but for hubs. The advantages of using a data vault modeling approach is that it scales easily because tables may be handled separately, and it clearly separates business rules from the data model. Also, there's more auditability. It's possible for you to track all the metadata. Although its implementation and design can be more complex, and thus the reason why this modeling option is not widely used, here's one example. So here you have a set of 3 hubs: the customer, order, and product hub. Then a table that links customer to order, product to order, and then 3 satellites that kind of are linked to the customer table to describe it, and linked to the order also, and also linked to the product hub. So this is just one example, and maybe in your data engineering journey you won't be exposed to Data Vault, but at least you know that this is another modeling approach. So thank you, and I'll see you in the next lesson. Welcome to this lesson. We've been mostly talking about data modeling options for structured data. Now let's talk about one modeling option more suited for ELT purposes, and that can be applied to data warehouses and data lakes, and even more suited for data lakehouses. This one is called medallion model, and it's a layering option which allows you to slowly enrich and clean your data before its final stage. This option offers you a clear separation between raw and refined data, and it can be used with a star schema or other schemas. It's more of an approach to deal with raw data and possible problems, and a focus on the structure of the model of your data. So the first layer of a medallion model is typically referred to as bronze layer, although you can also call it raw layer, as data is stored as it is ingested into this layer in a raw format. So this layer is all about data in its purest form. So like JSON dumps or CSV without exports without any cleaning at all. So after some processing can be done, and this data can be moved to a second or intermediate layer, which is the silver layer, or can also be called as stage or staging layer. Here it's expected that there are less duplicates. There was some data quality checks were applied and some validation. So from this layer, and after joining it and enriching it, we move data into the next one, which is the gold layer, the final layer. This is the last stage of your data before being used, and its final goal either for a dashboard, a report, or an analysis. That area was already fully transformed, clean, and it's completely ready for business insights to the right teams. So thank you, and I'll see you in the next lesson.
Welcome to this lesson. In here we are going to see the third example of this section, which is now related to the medallion model. So we've seen that the medallion model is more about ELTs or pipelines in which we extract, load, and then transform the data. And they are typically more related to a modern approach to data modeling, in which we progressively enrich the data before the end usage. In some cases, these can be applied to data warehouses, but it can also be applied to data lakes. So that's where we are going to focus this example on. So imagine that we have a data lake, and we can have one data lake folder that we're going to crawl like the raw layer. Okay, so this can also be called a bronze layer, or whatever denomination you want to give to the medallion model approach. But essentially, you will have 3 layers. So this will be, for example, the stage layer. This can be the curated layer. On another naming convention, it would be bronze, silver, and gold layers. And of course, that there will be data movements from one layer to the other. And typically these will be some operations like, I don't know, data transformations. We can have like data cleaning. We could have some other data processes here, and then typically here is data enrichment. So you can have here data integration, and here we'll have data aggregation, for example. So typically the processes that move data from one layer to the other are different, but the goal is or the final goal is that there's a gradual enrichment of data. So data in the last layer is ready to be used. Typically the usage will be, for example, for dashboard or or maybe some data analyst team, or someone or some teams that will be the end users of these data. And then sometimes you also have things like some teams getting data from the second layer, like operational teams or data scientist teams. So people can use these data from the raw, from the stage, or from the curated. Typically, this is where data is ready to be used by like having some structure, having some aggregations that were previously decided. Here, data is already integrated, and there could be uses like for machine learning or whatever. And then, of course, we'll have several data sources here that would be loading data like operational DB and some other like FTPs, for example. These can be all basically sending data, or there could be some pipelines grabbing data from these sources in their in its raw format to this first layer. So this would be an usage of a medallion model approach. So you'll have data sources that either there's a pipeline that gets data from there, or someone sends you directly the raw files to the raw layer folder. So this is all about raw data. So it's, there's no cleaning, there's no integration, there's no additional transformation, there's nothing. And then from this layer, there will be processes that will do that. So gradually you are enriching your data. So for example, you're cleaning missing values, you're adapting timestamps to be standardized, you're maybe making already some integration between raw data that arrive from different sources. And then someone can already pick that data on and possibly do some other transformations on their own side. So again, the ELT approach here. And then there's a final transformation. So for example, you'll aggregate like the orders for aggregated totals of revenue or whatever per day. So there will be data enrichment in the sense that you can bring new columns based on previous ones. So in this final layer, curated layer, or gold layer, whatever you want to call it, this is data ready for that has been modeled. It's ready for final usage, and it's more pristine and curated shape. So this is one example for a medallion model. You can also have these layers on a data warehouse. There's nothing forbidding you to do it. So yeah, just feel free to use this medallion model approach wherever your data architecture makes sense. And I hope you enjoyed this example and this lesson, and I'll definitely see you on the next one.
Welcome to this lecture. Now that you know about star schemas and fact tables and dimension tables, you might ask yourself, how would you know what tables to build? That's a great question. Enter the BEAM methodology. So BEAM stands for Business Event Analysis and Modeling, and it's a methodology created for helping with the data modeling process. Essentially, it is a set of rules and tips on how to reach out the best schema and set of tables that would help you carry the business analysis you need. It's a mix of data modeling and brainstorming, because apart from you, there will be other people involved in the process. Typically, your data clients, the business people will carry the analysis or look at the dashboards supported by the data model that you'll build. So this is a collaborative process. It starts with identifying the business events, which is a similar way to say that you'll need to know what facts are in the fact tables. Are you looking for sales or orders, or is it the checkout button push? Then you'll identify the dimensions. So the categories and characteristics that are important to be tracked in order for your business facts to have a clear context. If it's an order, it must come from someone, or so customer details could be a good idea here. Also, after this, you'll finally define the tables you'll have, which is the same to say that you'll design your star schema. And finally, this is not only a collaborative process, as it's also an iterative process. You'll receive feedback and you'll improve in your initial solution. So, and this can happen multiple times, of course. On a first step, while identifying the business events, you'll also need to define the granularity. This means that you want to track an order or the items on an order. In this case, this will be the main difference between having one line per order or multiple lines per order on your fact table. Dimensions can be trickier, and this is easy to understand why. So they are the crucial part of your analysis. This will allow you to segment clients, to know why certain products are sold more often, to know whether people buy more of your products in the summer or in the winter, finding the reason why there was a peak in sales in the last month. For that, BIM methodology helps you with a set of questions, the W's. So who buys, when, what did he or she bought, why just one or more items. So by answering these questions together with a business person or someone who knows that what analysis is needed to take action later, you'll be able to funnel your needs and get a clear picture of what dimensions you should consider, and also what columns will be included on your tables. Now let's jump into an example which will make things clearer and easier to understand. So thank you, and I'll see you in the next lesson. Welcome to this lesson. So after going through the theoretical part of the BIM methodology, let's now see a little more practical detail. So we're not diving here, since this methodology can help you not only define the tables you'll be setting up in your star schema, but also which columns are the most relevant ones, depending on the problem. Here we will just focus on the high-level modeling. So imagine that you're modeling your data after someone asked you that he or she wants an analysis on the product sales. So immediately you'll find that that's your business event. Just a sale. So a customer buys something. There will be for sure an order table or a sales table somewhere which will track these event sales, and that you'll use. And after that, you'll focus on the dimension tables. So you'll need to have some dimension tables for your analysis, and you'll start asking some questions. So who buys it? The customer buys it. What was bought? So the product was bought. One or more, depends. So this means that you'll need some table for the characteristics of the products, because probably your company won't have just one single product. Then when was it bought? So there should be somewhere a purchase timestamp. Where did the sale took place? So was it online? Is it in a particular physical store? Why was that bought? So why does the customer buys one product and not the other, for example? So this would be related to the product characteristics. And of course, how many products were in that sale? So it's just one item per sale, or more than one. So by answering these questions, you'll be able to conclude you'll need one fact table, which is let's call it sales fact. So whose granularity will be the sale. So one row per sale, which means that one sale can have one or more items, meaning that probably it's a good idea for you to have item quantity to this sales fact, which is a metric. So remember that the fact table will have a set of foreign keys to the other dimension tables, plus a set of metrics, and quantity of items in that sale could be a good metric. Also, the total value on the order will also be a good metric, and of course that will depend on the rest of the analysis, but you can add more metrics there. And the dimension tables, of course, you'll need dimension tables. So customer dimension, so you'll need some characteristics on the customer that will help you see what kind of products and correlate the products that you sell with the age of the customers or the region where they live. Also, one product dimension will be very useful. You'll need details on characteristics of the products, and also for example the store dimension. And then there's another dimension table that can be optional, which is the time dimension. This will happen a lot. So not only because time or date dimensions are hard to manage due to the holidays and time formats, etc., but also because nowadays SQL and data warehouse functionalities allow for swift and easy date time manipulation. So often you'll see that the time dimension can be optional and is not used so often as before. So this was just a simple example for you to understand and see in a practical way a way to look into fact table, dimension tables, and of course your star schema design. So thank you, and I'll see you in the next lesson. Welcome to this lesson. Often as a data engineer, you'll need to handle a lot of data. That means that most of your struggle will be on getting to data fast rather than the burden of setting up a good model for your data. There are a few handful tools and options that can be of help here. So in this lesson, we'll see a few ones, starting with indexes. So indexes do just that. They improve the speed of data retrieval because they are ways to help the database locate rows, easily avoiding full table scans. There are several types of indexes, such as the unique, the clustered, and the non-clustered. We won't dive deeper here, don't worry. And also there are the possibility of composite indexes, which are indexes that combine more than one column. As a data engineer, you should be looking for setting up indexes on columns which are often the target of your where clauses, your joins, or your group bys. Also on columns which are often used for ordering data, like let's say a timestamp, for example, and also columns which have many unique numbers like IDs. However, don't be tempted to use a lot of indexes because they will actually slow down insert and delete and update operations, which are useful for your ETL pipelines. Also, let's rebuild them often because things sometimes change and indexes can be affected by those changes. Another tool at your disposal is the partitions. So these divide tables logically into smaller partitions which facilitate the scope of a query, for example. So in some cases, data warehouses will offer data retrievals in parallel, thus making your queries even faster if they use partitions. So let's see an example now. Imagine that you had a partition on a specific table on the user ID, just like this. So all of the users with user IDs lower or equal to 500 are in one partition. The users with ID between 500 and 1,000 are on another one, and users with user ID bigger than 1,000 are in yet another partition. So 3 partitions. In this setup, once you apply this query, so which will look for the user with the user ID 750, the data warehouse engine will look into only the second partition, because it's where the data belonging to the range of the user ID 500 and 1000 is. So this means that the other partitions will be skipped and your results will arrive faster. Another important element in optimizing your BI solution are the materialized views. So unlike views, materialized views store data physically, since they are the materialization of a query. They can be set up for automatically refreshes, which allow query results to be pre-computed and available for BI tools. Yet another tool is the normalized tables. They combine data from multiple tables and they sacrifice space for query performance. This can be used when data is big, although remember that your table will use a lot of space in your data warehouse. I hope you enjoyed this small set of performance enhancing options for your data warehouse. I'm sure that you'll find them useful on your data engineering journey. So thank you, and I'll see you in the next video. So welcome to this section sum up. We've covered a lot of important concepts for a data engineer. Essentially, we focused on one of the main tasks of a data engineer, which is to model data. And in modeling data, the modeling data stage occurs on your pipeline. Somewhere in your pipeline, you'll need to model your data. But to model your data, you need to know exactly what options for data modeling exist. And we've covered star schemas, snowflake schemas, data vaults, also the medallion model, which is applied to not exactly only to data warehouses. So after modeling, you'll have your final data model, but you know that sometimes there will be some performance issues, and we have covered also some optimization tricks. So I think that this is one of the central sections of this course, following the previous one on the data pipelines, data sources, and data repositories. With these two sections, you will be able to have very basic, very strong and solid basis for being a good data engineer. So thank you, and I'll see you in the next section. Welcome to section 6. Congrats on making it this far. It means you dedicated enough time to study through the basics of data engineering. And you've learned a lot on your way here. You know about cloud and its services, you know about data pipelines, data types, and data sources and repositories. And recently you learned about data modeling, so now it's time to put all of that in practice. In this section, you will be exposed to some techniques to tackle data wrangling, which is basically working with data and taking the most out of it. This will include cleaning, transforming, and validating data. It's an important section, and it completes most of the technical aspects of working with data. Expect some SQL and Python to show here and there, but remember that this is not a SQL or a Python-centered course. So thank you, and I'll see you in the next video. Welcome to this video. Like I said before, section 6 is all about getting the most out of your data. We will start with the definition of data wrangling, which is the name of this section. And then we will jump into one of the activities that you will perform a lot on your career, data cleaning. Real world data often has a lot of problems, so cleaning it will be certainly part of your days. Then we will jump into data transformations, where we will learn the most common transformations applied to data. And in the end of the section, we will focus on data validation. So I hope you enjoy this section and that you take the most out of it. So thank you, and I'll see you in the next video. Welcome to this lesson. So what is data wrangling? In simple terms, it's a set of processes you implement to get the most out of your data. A set of transformations and operations over your data to enhance it, make it better and more suitable for analysis. It can be defined more broadly as a way to bring data from its raw form into a structured one by implementing a set of steps that include cleaning and transforming it. For these, you'll need tools, and the most common ones are SQL, Python, of course, specifically pandas or NumPy, which are two libraries that you'll often use. Then when scale of data is involved, Spark will also be an additional tool you can be exposed to as well. More recently, and gaining a lot of traction, dbt or data build tool, which is an excellent support to help you with transformations and to implement some data quality checks as well. And then there are other libraries such as Sodo or Great Expectations that can also help you with data validation. In the next few videos, we will dive deeper into some of the data wrangling operations you may find useful to be applied to your data. So stay tuned and take the most out of those videos. Thank you, and I'll see you in the next lesson. Welcome to this lesson. We've talked a lot about data, and you know now every basic concept to start your own data models. And now comes the bad part. Yeah, data is not perfect at all. I've seen everything: missing data, wrong data types, wrong data formats, big data sets from which you can extract only a handful of good rows of data. So data accuracy, completeness, and consistency, they are not easy to achieve in the real world. So the first main big data wrangling process that we are going to talk about is, of course, the data cleaning process. And data cleaning is a set of transformations you apply to your data to ensure that it is as accurate as possible, as complete as possible, and as consistent as possible. So now let's dig deeper into these three of the most common data cleaning problems. Thank you, and I'll see you in the next video. Welcome to this lecture. Let's now talk about data deduplication, which is the data cleaning process of removing duplicate entries from your data. Of course, often in real-world data sets, you'll have data will have duplicates. Sometimes because of errors in the operational world, or unclear procedures, or even bad requirements. You can have one entry with more than one row in a table. It can happen to both events or categorical tables, so there are a lot of data inspection and monitoring that you should be doing. In fact, there's even kind of a split here. If this process is automated, it's often called data cleaning, while if it's more on manual checks in place, that it can be called data cleansing. Data deduplication can be tackled normally with SQL or Python code. In the first one, there's a way to build a view or to apply the word distinct in a way to avoid entries in which one particular column needs to be unique. This is not an ideal solution, but it works when the duplicate entries can be tracked with only one column, like an ID, for example. However, if the duplicates are defined by a subset of columns like name and surname, this keyword won't suffice. So there's another way, which is the row number function, a window function SQL has, and that help you track duplicates when more than one column needs to be checked for a single value. In the first case, the SQL query will be relatively simple, since you just have to add the keyword distinct to your query. Here in this example, you will select distinct rows by ID. It means that if there's a duplicate with two different persons on a table with the same ID, you'll drop one of them. Another issue, aside from what I referred in the previous slide, is that there's not exactly a way to specify what ID is the right one on those two rows which have the same ID. Also, for example, if you're using distinct on name and you have two rows with the same name, but one of them starts with a capital and the other one doesn't, then both records are kept. For cases such as these, there's the alternative, or you'll have to cleanse them manually. The other alternative, like previously mentioned, is the row number window function, available in most SQL versions, if not all. To apply, you'll add a new column with the result of the row number function, which basically is a number of rows according to the partitions that you create and how you order them. So if you have three columns, ID, first name, and last name, you can use those in partitions. which will identify every row that has similar values in those columns. And it will order them by what you define there on the ordered by part. After that, you include this on your CTE and just filter for the rows which have the row number as the first one. So these are the most common ways to remove duplicates with SQL. Now let's see the Python approach to handle these cases. Let's imagine that we have these datasets, and as you can see, lines 2 and 3 are the same, they are duplicates. But also you can see that cities in line 1 and 4 are also the same. So using Python, pandas library, which is one of the most relevant Python libraries to work with data, you can either drop duplicates with a single command or tailor the command to drop duplicates according to each column. So here we duplicate in a single command, and here we create subsets of each column that we want to focus on. Pandas is very flexible, so you can sort things out easily and drop the cases you want to drop. So that's all on one of the most common processes of data cleaning, dropping duplicates. Thank you, and I'll see you in the next lesson. One important process in data cleaning activities is missing data handling. Yes, most of the times your data will be incomplete, and it will be incomplete in different ways. One entire entry can be missing, or it can be there, but almost all of its columns are missing. Depending on the case, you'll need to be using imputation of data, which essentially means to create data to replace what's missing. But let's see what are all of the approaches that you can use when there's missing data. First, and the easier one, is nothing. Just ignore it. Like, drop all the rows which have nulls. This is a valid approach, but use it carefully, since you might end up with just a few rows available if you have a lot of missing entries. The second option is to create data where it is missing in a process called data imputation. This option allows you to retain most of your data by just replacing the missing values by something. This something can be a constant value or a placeholder. It can be a statistical measure like the mean or the median or the mode, or you can use some more advanced features like interpolation, or even using machine learning to guess what values should be there but aren't because they are missing. Let's now see some examples. Here's a data set with missing data. Some of the columns and most of its rows have missing data, which means that if you use the first option we talked about, which simply ignores missing data and deletes every row with a missing value, you would end up with the first and the second to last row. So let's now see the other options. Let's first start with the statistical option. So we're using the mean of the values that exist in the age column to fill in those values in that same column that are missing. This means that we are assuming that the person whose age we weren't able to calculate as an age which is the average of the existing ones. This is a bold assumption, but you can make these kind of assumptions if they make sense in the context of your business. Then the second assumption we're making is that the salaries that are missing are replaced by the median, which means that we are assuming that they are in the middle of the salary distribution. Finally, for the categorical variable, which is gender, we assume that the missing genders are replaced by the most common gender on the dataset. So let's see the result of applying these very simple Python and pandas methods. You can now see that the dataset doesn't have any missing values. And you can also see that handling missing values isn't exactly hard. What's harder is to make the right business assumptions. Remember, missing values will affect your business decisions and the conclusions you reach with your data analysis. But the values you will replace those missing values for will also have a big impact. So make sure you know the business well enough and that you consult with business experts before making too bold assumptions. Thank you, and I'll see you in the next video. Welcome to this lesson. Another problem that you will often find in data is related to inconsistent formats or lack of standardization. Sometimes it's an issue with capitalization. Some entries start with capital letters while others don't. Sometimes it's date formats. I would say that this is a very common case. Then you also can have different currencies, which if we ignored can generate issues with totals, for example. Let's focus on the particular case of the time formats. This can occur often, like I said, and can be challenging. Casting functions can be of help, and there's a lot of also libraries that can help you tackle these challenges. And sometimes even you might need to use regex expressions. They are also a good option, although harder to implement. But once you understand regex notation, this can be very helpful. Let's see a small example with Python. So here you can see that the column timestamp has two different formats. The first one is the one adopted, let's say, by your company, and you should always confirm that. What's the standard notation for a timestamp, for example, for a date field? In this case, we will convert the second row value using this datetime library in Python to help you, and you can see that the value return is on the right format now. So these kind of actions are often incorporated in the data pipelines you build, whether you're handling ELT or ETL. Probably there would be a step in the staging areas to look and fix these kind of date format issues, but they can also be handled right on the ingestion phase. So I hope you enjoyed this little lesson. Thank you, and I'll see you in the next video.
We're going to dive deeper into data cleaning with SQL on this fourth example that we have in the course. So we will see a specific data set. This is a very small data set, just for the sake of this example. And you can see that the data set has a few issues like nulls. You can also see that there are countries which are actually not countries. You can see that there are income entries which have no value. You can also see that line or the customer ID with 8 is as a duplicate row, and you can also see that there's a country which is called Great Britain, but then there's another entry for UK. So we are going to be solving these issues with SQL. I've imported the data set into Snowflake. So Snowflake is a data warehouse in the cloud, and we can do these sort of transformations using SQL right here. So you see that this is the same data set. So you can see that there's a few entries in nulls. There's also an email, which is not an email actually. So you can also find some incomes that can be replaced. The issue with the city, which is in the country column. So let's go into the data cleaning process for this. So the database is exercise 3, and then we have the tables right here on one table, which is raw customer, where it's the data that I loaded into. So starting with maybe the cleaning part. So cleaning part 1 for the duplication. So let's first start with actually identifying the duplicates. We know already that there's an entry, but let's see if there's more. So let's just count the number of of records per customer ID. Let me just copy these, and then let's by and order. Okay, so if we execute this query, we'll see that line 8, or the customer ID 8, has 2 entries, so it should have only 1. So for that, we will create a second table. So we will always creating a new data set over the cleaning processes that we will have. So let's create a table called, instead of raw customer, let's say customer part 1. And we are going to clean the data set. So if I run this again, you can see that the all entry is the same. So this is actually a duplicate. So sometimes you can have like duplicate columns, but this could be a different customer, but it's not the case. So for this particular case, if I do this, it will actually create a table without the duplicates, because it will apply this distinct keyword to the table with duplicates. And we can now, if I refresh these, you can now see that there's customer part 1, and if I apply the same query to customer part 1 table, you can see that now the duplicates are eliminated. I can even take a look at the table itself. I do this, I'll be able to see that now. Yeah, so there's only 1/8 as a customer ID. So this one is solved. I can there's other ways to apply these this kind of data cleaning. So we can do again the duplication 1.2, so the second version of this. So we can also create again a table. Let's call it option 2, and we will use now a window function for these. So I'll just create where's the name? Okay, this is the name of the table. So I'll create this, and then I'll just do a row number, which is a window function, over, and have this partition by customer ID, and I want to qualify it as 1. So this will basically go over the rows, and we'll partition by customer ID, and we'll find that for customer ID number 8, it will have a duplicate. So for that particular case, there will be a second row which will have a number 2 here, and won't qualify these because we are only checking for row numbers ones for the first ones. So now I can create this table and then check order by ID. Okay, and now I'm going to create this other table, and if I go and grab this code and apply it to this option 2, you can see that for customer ID 8, we also only have one row. So there's always several ways for us to go over these issues of duplicates and fix them. So I just present you with 2 options for using SQL, but for example, in Python, there are functions that will do this automatically for you. Now let's take a look at the, let's choose this table and continue from there and see exactly what other problems we can encounter with this data set, and then start addressing them. So one of the other issues that I forgot about was the age. So this was derived by some birth date that the customers probably included. Now let's see that -5 is not a real age, 120 is probably also some error. So let's just fix that and probably just add these values or add nulls to these values so that we can so let's fix age, so that and we can then fix this issue. So no, that's no. At least let's fix this one. Okay, and now we can check this table and see that now there's a null here, which is much better than a -5 as an age. Let's leave this one and do the other part. So for example, we can now fix the email. So there's only one email that doesn't have the domain at email.com. So let's fix emails. So we will do another update to this one. So in this case, I told you that we are going to be creating always be creating a new table, but we're now fixing directly on these tables. So let's just fill these as a concatenation of maybe the name of the email, and let's have this at email.com. So this will concat what exists here with the domain of the email. So, and we will do this where domain, where email is not like and doesn't have the at. So this will basically update only the entries where the email value doesn't have an at. So we can then check, we can see that there was one row updated. We can check here again, and we will see that there's no, so the issue was fixed. So now all the emails, at least the ones that we know, they have domain. So let's now fix probably the income. So imagine that we want the incomes that, and something that I haven't told you. So when we want to clean data and assume that we don't want to delete things with null, so for example, not dropping these or dropping could be a strategy. So we always have to think about the strategy to replace null values, either to drop all of the old line or the old column or whatever, but also if we want to replace that is doing some imputation to missing values, we have to know exactly what should we replace, which value should we add as part of the null replacement strategy. And in this case, we are going to actually use the average value for this. So let's go over here, and we will replace the income. Set income equal to, and we will select the average value, average of income from here. From here as where the income is not null. Because otherwise, and we can do this, so if we run this query, we'll get, this is the average value of the income. If we don't have these, it won't return a value, and I want to replace the values where the income is null. So if I run this, it updated two rows, and if I run again these, I'll see that there's an income here, which was replaced by the average value of the available entries. And now we can just fix the country. So we will just do this one. So because these are very repetitive update statements to the same table. So let's just focus on the country and say it's USA, where the country is New York. And we will just fix these last step, and we can check again the data set and see that that issue was also fixed. So of course that there are more operations that we can do. We can derive emails, we can just choose to delete all the entries which have null values. But again, that's part of the strategy that you will have to think of before starting the cleaning process. So here, the focus of this exercise was more into the processes, that the computing processes that we use to actually update and generate new data sets, and slowly trying to clean the data that was wrong. So problems like these will always come up, and what I advise you to is just to do some similar exercise in the beginning, that it will be similar to this. So just grab some sample of your data, just take a look at the operations that you can do to clean it, and then try to apply those operations at scale, and also embed those operations on your data pipeline, because typically the data cleaning process will be part of your pipeline. So you want these things to be automated. Of course, that if you work as a data analyst instead of working as a data engineer, or as a data scientist instead of a data engineer, you will face these kind of cleanups more manual on your exploratory data analysis, or on your initial solutions to your machine learning problems. But as a data engineer, just remember that these kind of operations need to be automated, so they should be part of your pipeline. So in the beginning, you will explore a little your data and come up with the right operations, and if needed, also check with business people, check with someone that knows exactly if, for example, if an average income is acceptable to be replaced or input to be evaluated as imputation to missing values on income, or if not, that your strategy needs to be revised. So I hope you enjoy this very simple exercise, and I'll see you in the next lesson.
Welcome to this lesson. Data transformation is the process of bringing data to the form or structure which is the most appropriate for your goals. You would be too lucky if source data is already organized and in a tidy and beautiful manner. What's the most common is exactly the opposite. So this means that you'll need to apply transformations to your data, from simply changing a format to adding a column or aggregating rows in a specific way. There are a lot of data transformation operations that you can execute over your data to get to the final structure, or the structure that is more appropriate for your analysis. In the following set of videos, we will talk about some of the most common and simple ones. So I hope that you enjoy. Thank you, and I'll see you in the next lecture. Welcome to this lesson. We start this data transformation part with one of the most simple transformations that you need to apply: sorting. Sometimes you just need that to sort your data in an ascending or descending way to do your analysis and take your conclusions. This can be often directly applied on the dashboard side of a BI tool, but sometimes sorting is required inside your pipeline. It is a very simple operation which can be done with simple commands like this one in Pandas Python library, or this one in SQL. These operations change the order in which the rows are presented, but they don't alter the content or the shape of your data. They are very simple to be applied, but don't forget that sometimes if your data is big, this can be computationally expensive. Next, we will see one type of transformation that alter the content or the shape of your data. So thank you, and I'll see you in the next video. Welcome to this video. Aggregations are a very, very common type of transformations in the analytics world. It is where you often come up with metrics that make sense for business to take a look at. These metrics typically reside around totals or other statistical concepts like the mean or the maximum or minimum values. There could also be counts involved and sometimes filters as well, but these are the most common aggregation types. Here's a very simple example with an aggregation by category, which could be needed by or requested to you by someone in the business side. These transformations can be simple or more complex depending on the goal and on the number of metrics included. here's the SQL example. So you can see that the category is part of the group by statement, which we're looking into data by category. And the metrics that are involved here are the total value. So you sum the value, the average value, and you make an average out of that. And of course, there's a count on the values as well. And the Python equivalent to generate a total by category on the previous data set is this one, and another one to include both the mean and the count of values. Contrary to the previous sorting operation, here we can see that both the content and the shape of the dataset is altered. So that this makes these transformations more complex to be applied, and also sometimes more computational power is needed to perform these operations, again, depending on the size of the data. So thank you, and I'll see you in the next lesson. Welcome to this lecture. Applying filters is another type of data transformation, one operation that affects the shape of your initial dataset. However, this doesn't affect your content, only if it is applied together with other operations. In this simple data transformation process, you'll create another dataset which includes a subset of your data. And for that, you'll either use a where clause or an having clause in SQL. Here you have a very simple example in SQL where you filter the data in the dummy data table, and you only get a subset in which the entries have a value which is higher than 20. And here you have the same operation, but using Pandas Python library. They achieve exactly the same results, and they are just both two different ways to get to the same goals using different programming languages. This is a very simple transformation, as you can see, and even the code to perform it is very simple, but you'll find them very, very useful in your data engineering journey. So now let's jump to a more difficult transformation, which includes window functions. Thank you, and I'll see you in the next section. Welcome to this lesson. Window functions are very useful in SQL, and they also have their equivalent in Python. These functions allow you to transform your data by performing calculations across a partition or a subset of a column. These calculations include cumulative summations, first values, last values, next values, and you'll find these particularly useful when you've got a request for some complex queries that involve latest values or the next values of something. You'll find these particularly useful in those situations. They're not very easy to apply, but we will see an example in one of our next lessons. Here's a data set that is a very simple example. So we have two categories and a value, and with this SQL query with a window function, we can get a cumulative summation of the column value with a partition by category, which is almost the same as this code here in Python that would get you to the same value. You can see that you've got 10, which is the first value of the category A, and 30, which is the summation of 10 plus 20, which is the second value of the category A, if we get back here to the data set. Okay, so these window functions, they are typically including the aggregate functions like summation, average, or counts. They have you also have ranking functions like the row number, the rank, or the percentile rank. Value functions like lag or lead or last value. These are very powerful and useful in SQL. So explore them deeper, and they'll also be very useful for your data engineering career. So thank you, and I'll see you in the next video. Welcome to this lesson. Data validation can be defined as the process of ensuring that your data has quality. This often means that validation happens after data cleaning, where you fix most of your data issues. So here you will find, try to reduce and eliminate as much as possible of data processing errors that could have occurred on your pipelines. This process exists to assure some trust in the analytical process, meaning that you have some standards that are enforced in your data in terms of quality, consistency, and completeness. This will assure people who work with your team that your data has quality and that there are at least data quality checks in place. The key goals of data validation are to assure that data is correct and free from errors, meaning that you want your data to have accuracy. Also, that your data has to be consistent, meaning that it follows a uniform format across all sources or all repositories. Data should also be complete, since all of the data fields need to be populated, and also assuring that the relationship between data elements is valid, which is the same to say that your data has integrity. And finally, of course, that you need to assure after this data validation process, or the goal of the data validation process is also to assure that your data is relevant to the business. Some good validation techniques include schema validation, so kind of looking at the table and ensure that it follows a set of columns that was previously defined. Domain validation, range validation. You can, for instance, look at one column and check if the numbers inside it is within a range acceptable for your business. For example, one good example here would be value of your products. The range of that column cannot exceed the maximum value that you have your product selling for. Also, some good some uniqueness and checks and also null checks are also important to have on your data pipeline, or at least on the data validation part, to make sure that your values, which need to be unique, are in fact unique, and that you don't have null values, meaning that your data is complete. In terms of tools to apply these data validation techniques, the most typical way is to assure that data is valid through some custom SQL queries or even some Python script, which includes, of course, pandas. But then there's other Python libraries or frameworks that can help you, like Great Expectations or Soda. Well, this was all about data validation, but the truth is that this video finishes this whole series of section 6, which was focused on data wrangling. So thank you. I hope you enjoyed this section, and I'll see you in the next one. Welcome to this video. Before jumping into the next section, let's quickly sum up what happened in this one. So this section was all about data wrangling, or data transformations, and the process of cleaning data and validating that data as well. So all of these set of operations that manipulate your data in order for you to get the most out of it and to benefit the business with new findings or insights about what's happening around your company. We talked a lot about operations around data, which is the same of almost the same definition of data wrangling. We talked also a lot about data cleaning, so all from how to handle missing data to make sure that formats are in the right way, or the right format that you define. Also, we talked about data transformation, so at least briefly and somehow in a theoretical manner. And also we talked about data validation and the importance of making sure that your data is valid, is complete, is ready for generating insights on the business side, and also that to make sure that this data is reliable on every sort of way. So I hope that you enjoyed this section, and I'll see you in the next one. Welcome to section 7, the last one of this course. Congrats, of course, on making it so far. Right now, and for sure, you have a lot of new concepts to think of, and you know a lot about data, the data engineering ecosystem, data pipelines, data modeling, and data itself. Also, you already know that in a real world environment, you won't be exposed to just one data pipeline. It will be to much more. So that's essentially the reason why you'll need to know about data pipeline orchestration. Hence the reason why the seventh section exists in this course. Here you'll learn about the reasons why, apart from this one, we have to orchestrate data pipelines, and some tools that we can use to do just that. So welcome, and I see you in the next video. Welcome to this lesson. Section 7 is the last section of this course, and it's all about orchestration of data pipelines, like we said before. So we will start with the definition of what is exactly orchestrating data pipelines. Then we will move into Airflow, which is one of the many orchestrator tools that are available out there. First, we will do an introduction, then for a brief but kind of deep dive into some of its basic concepts like DAGs and tasks and the dependencies between the tasks. Then we will talk about operators and sensors. Finally, we will see some examples of the Airflow UI so that you know what you can count on with Airflow. Remember, this is just an introduction to Airflow, not a full course on it. So again, Airflow is one of the many orchestrators available, but it's also one of the most common used. But yeah, this is just an introduction, so I hope you enjoy this section and that you take the most out of it, and by the end of it you should be able to know why exactly do you need orchestration and how can you do that with Airflow. So thank you, and I'll see you in the next lesson. Welcome to this lesson. Now that you know about data pipelines and the most important and relevant data processing operations, we've talked a lot about data cleaning, about data transformations, about filterings and aggregations. We also talked about data modeling. So now it's important to focus on handling and managing a lot of different pipelines, which is the base scenario for any data engineer. This is where data pipelines orchestration comes in. So this process helps you coordinate and automate data pipelines in an efficient and reliable way. This often includes managing dependencies between tasks, schedule arrangements, and how can you handle failing tasks and retries. Basically, orchestration is related to how do you start one particular task before the next one. How can you schedule different pipelines to be executed automatically? And if some of them or a part of them fail, how can you handle that also on an automated way? So you can essentially think of orchestration like a way to allow you to sleep well at night if you handle hundreds of pipelines, because the orchestrator will help you with the automation part. It will trigger the right pipelines at the right schedule that you define. It will make sure that all of the subtasks they have are executed in the right order that you have defined, and it will even solve possible failures the way you tell it to. There are many orchestrators, but the most well-known one is Airflow. It's kind of the standard in data engineering. However, there are others like Luigi or Daxer or Perfect, which are also good options. And of course, that cloud services providers, they also have some native options like AWS Step Functions, Google Cloud Composer, which can also include Airflow. So the question you might be asking is, can I do this can I manage data pipelines without an orchestration? Yes, you can. However, orchestrators will help you a lot. They make managing tasks become very easy. They also help you with monitoring and retries handling by themselves. They ensure scalability because you can understand or trying to monitor the performance of 10 data pipelines is much easier than doing the same thing for hundreds and hundreds of them. Also, orchestrators make it easy to handle pipelines whose tasks touch multiple different systems, so different sources. You can have one pipeline that gets data from a data lake and also from a data warehouse at the same time, or in different tasks. So orchestrators can also help you there. So using an orchestrator is essentially a must nowadays. So let's now dive a little deeper into one of the main ones, which is Airflow. So thank you, and I'll see you in the next video. Welcome to this video. So now that you know that you need an orchestrator to help you managing and monitoring all the data pipelines that you will be working on, let's now dig a little deeper into one of the most famous and useful ones, which is Airflow. Apache Airflow is an open source orchestrator. It's heavily used on the industry, so for sure that you will be exposed to it on your data engineering ecosystem. So one of the first reasons why you'll need Airflow is because you need an orchestrator. Then you'll use Airflow because it is scalable and reliable. You can easily manage a lot of pipelines with it. Also, there's a big community around Airflow, and you'll quickly adapt to it because it's coded in Python. And finally, it has a very friendly UI that helps you monitoring all of the pipelines that you build. Airflow has several components, and although you won't need to know about all of them or all of their details, but it will be useful for you to know generally how it works. So Airflow central pieces are the scheduler, the workers, and the metadata database. These work on a team that allows you to be sure that pipelines will be triggered at the exact time that you want them to, that they will be executed by some computer without your intervention, and that you'll be updated of the status of your jobs on your UI. Let's see now these and other components in more detail. So starting with the metadata database. So this is a Airflow central repository. It stores metadata related to data pipeline schedules and task history. Essentially, it is a place where where everything you need is stored. So every time that you develop a DAG, which is essentially just this set of tasks in your data pipeline, and add it to a DAGs folder, which is where the metadata database will read and parse your DAGs from, storing which ones will run when. So also this metadata database will connect to the UI and to the scheduler. The scheduler is the component that triggers the tasks at the right time. So it instantiates DAG runs and the tasks and checks the dependencies between every DAG's tasks. This is the component responsible for making sure that at the time you define your Airflow pipeline to be triggered, it will be in fact triggered. The executor is the component responsible for grabbing tasks from the scheduler's queue and then send them to the workers for execution. So essentially, the scheduler checks the time at when it's time to start a certain pipeline. It will trigger them, which means that it will create an instance of it and its tasks and add it to a queue for execution, and then will grab from the queue and assigns to a free worker. The worker is the component which is responsible for executing the tasks and of course communicating their statuses to the metadata database, from which the web server will send data to the UI. And that's when you know exactly what status are your DAGs at. So the web server is also checks for the metadata database for new pipelines and manages all of the communication to and from the UI. Aside from the scheduler, there's another component which can also trigger DAGs. This one is the triggerer, and it handles asynchronous tasks. It is used for in deferred tasks and with pipelines which await an external condition to be ran. So these were the essentials on the Airflow components and how they communicate and handle the workload that allow your pipelines to run. This is just an introductory lesson, so be prepared to dig deeper in the future if you want to know more about Airflow and its components. So thank you, and I'll see you in the next video.
Welcome to this lesson, in which we're going to make a quick tour on Apache Airflow. So Apache Airflow is an orchestrator, but you can interact with it through the web server, through the web browser that you use, since it has a web server that kind of shows you a web interface for you to see your DAGs and also interact with them in some ways. So this is Apache Airflow. This is I have this instance running on my computer. You can see that this is the front page. So sometimes if you want to refresh and see the fresh metadata about your tags, just press the Airflow button here, and then you see a list of tags. So these tags are built with code. We're going to see exactly how can we build these data pipelines that are called typically DAGs in Airflow, mainly because they are directed acyclic graphs, so a sequence of tasks that need to be done somewhere. You can see that some are paused, some are unpaused, and you can filter. You have some filters here. You can even add some tags. You can see that these have all the same 2 tags. You can search by name if you know the name. It's important for you to keep a naming convention on these DAGs so that you can follow some logic within your team. And then also you can see more details about the DAG runs for these particular DAGs. You can see that some were running as successful, some other failed, some are now paused. So they're not running. You can see also the schedule. Only this one has a schedule to run daily, but you can define exactly the minutes in which you want these DAGs to run and how often will they run throughout the day or a week or a month or whatever. You can see the data on or metadata on the last run of the DAG, the next run, and also the recent tasks of the most recent run. And you can see that there are some details on the statuses of the tasks which run on Airflow. Then you'll have some action buttons. This will not delete the DAG itself. It will delete the metadata about the DAG. You only delete DAGs if you go to the DAGs folder of Airflow and remove the Python code from there. And you can trigger the DAGs manually. You can also set these to auto refresh. Here you can see some warnings. Sometimes there's bug issues on your code, and you can also see errors in red in here. These are mostly warnings because of the installation that I've made. And then, yeah, if you we will have another lesson on these, but if you open another tab on the details, you see some details. You can see the graph. This DAG only has one task, but you can have more. You can visualize more data about the DAGs in Airflow. This is just a quick intro. We will get back to these views and some other options that you can see data related to your DAGs on the next on one of the next lessons. So I hope you enjoyed this one. Thank you.
Welcome to this lecture. In the previous video, I talked a lot about the concept of Airflow DAGs. In this one, I'll focus on that concept and also on other ones which are important for you to know on your contact with Airflow. So first, what are Airflow DAGs? They stand for direct acyclical graphs, and a directed acyclical graph doesn't have circles, and it's a set of tasks that follow a direction. And for those who are not that familiar with a graph, this is a mathematical representation of a set of nodes and edges that connect those nodes. The Airflow DAGs define the workflow of a specific pipeline, indicating each set of tasks and the dependencies between those tasks. And it typically also includes the information of on scheduling of the pipeline that will be then checked by the Airflow scheduler. Of course, that it also includes other information, but we will see it briefly. So here's an example of an Airflow DAG. Here you can see 3 tasks, which are the graphs nodes, and they are connected by edges, which in this case will be the dependencies between the tasks. As you can see, the graph is directed with task 2 and 3 starting after task 1 and the third task after the second task. Also, there's no cycles, meaning that the flow doesn't come back to a previous task. So it's always going from task 1 to task 3. Let's now see another example of another DAG. Here we have a very different graph, in which task 2 A and task 2B are done in parallel after task 1. This is also a DAG because it's still a directed acyclical graph. Simply the two tasks are done at the same time, or at least they start at the same time. But after they're done, task 3 will start. So there's still a flow from task 1 to task 3. DAGs are fully coded in Python, and their file must be added to the DAGs folder, to the Airflow DAGs folder on your Airflow instance. From there, the metadata table will database will add them and also the web server will populate them into the Airflow UI. A DAG can be triggered manually through the UI, so you can push a button and trigger a DAG, but it can also be time-based or event-dependent. The schedules of the DAGs follow cron expressions, which are expressions that contain 5 fields: one for the minutes, one for the hours, one for the day of the month, one for the month, and one for the day of the week. With these 5 fields, you'll be able to define all sorts of schedules, from DAGs that run every day at the same time to DAGs that run just once per month or once per week or twice per hour. For that, and besides the numbers, you'll also rely on a set of symbols like the asterisk, which represent any value, the comma, which allows you to specify more than one value for the same field, an hyphen, which allow you to specify a range of values, and the slash, which allows you to define step values. Let's see a few examples for this to become clearer. So imagine that you want to run a DAG for a pipeline which runs every day at midnight. So on the minutes field, you have to input 30, and on the hours 0, because it's midnight. And then you want it to run every day, so you leave the rest as an asterisk. On another example, let's imagine that the pipeline must run at 45 past midday and at 45 past 3 p.m. and only on weekdays. So this means that you'll have to add a range of days of the week from 1 to 5 on the weekdays field, and add 45 in the minute slot, and then give a list of hours with a comma separating with hour 12 and 15. Because that's when they will be running. So twice per day on the weekdays, always on 45 minutes, just for the hour 12 and 15. And finally, a third example, which runs every 10 minutes only on the month of August. So this means that you'll need to input 8 on the month field, and then a step of 10 minutes on the minute slot. So now that you know a little about these how to schedule DAGs, which means that you know how to set up time-dependent DAGs, let's now see another type of triggering event or condition, which leads us to the event-based DAG. So in fact, DAGs can also be triggered by an event, like Airflow sensors, which can, for example, await for certain files to show up somewhere and then trigger the pipeline. These use a trigger run operator, and there could also be DAGs that are triggered externally through an API. Apart from these, deferrable operators also exist, and Airflow datasets are a more recent way of scheduling DAGs based on data consumption. So these event-based DAGs are less frequent than the time-based ones, but you can also be exposed to them on your data engineering journey. Next, we will dig into Airflow tasks and their dependencies. So I hope you enjoy this long lesson, and thank you. I'll see you in the next video. Welcome to this lesson. Now that you know about Airflow components and what are Airflow DAGs, let's look into the building blocks of them. So the tasks. Tasks are single units of work on a DAG. So they are the fundamental part of Airflow workflow, and they represent a specific operation that needs to be executed. As you've seen with one of the previous examples, tasks can be sequential or in parallel, meaning that some of them might start at the same time, some others are just start only after the first one finishes. If you don't explicitly define a sequential task, then Airflow will consider that all of the tasks will run in parallel. Parallel tasks can be defined inside squared brackets and separated by commas. Sequential tasks are defined with double arrows. And you can either define them in one way or the other, whether it's pointing to the right and the left, it's the same thing. Regular parentheses can help you with more complex task definitions. Some tasks can also be dependent on the same tasks, or the same task of a previous task run or DAG run. There might be cases in which you want to process some data if the previous task executed on the previous DAG run finished that task already. In that case, you can set depends on past equals to true. The task will then wait for the previous one on the previous day and hopes that it finished successfully so that it can start. Some tasks can also be dependent on something called trigger rules, which define the reason why a task may start. For example, you can define one task to start if all the tasks in a parallel part before it has succeeded, or that trigger rule can be all success, for example. So to sum up, tasks can depend on the previous task, success or failure. They can depend on external events like a previous DAG run being successful and having finished, and they can be also executed sequentially or in parallel. Okay? So tasks are instances of an operator. This means essentially that you don't need to start everything from scratch, and that someone on the community have already created a handful of operators that can be used for actions like, for example, calling a Python script or a shell script, or that connects to a certain data lake or to a data warehouse, or that loads some task from somewhere. Tasks also have statuses, since not all of them are successful. So some of their statuses are running or schedule, success or fail, like I said before, skipped or up for retry, and deferred. Let's now see how you can define tasks. So we've previously seen that it's through Python code, and but we'll see now a step-by-step. First, you'll have to import libraries. Then you define default arguments for the DAG. Then you define the DAG itself, and then you define the set of tasks, and then you set the task dependencies. First, let's see the first part. So here is an example in which you import libraries. That means that you import the Airflow library, or specifically you import the DAG out of the Airflow library. Here you also can see that you are importing two operators, which is a Python operator and bash operator. And then you can also import other components that you'll be using on your code from other libraries. And they can be outside of Airflow scope. Next, you define the default argument. So you can define the retry policy, for example, and you can also define a list of emails that will receive a notification every time there's a failure. And you can define a set of rules to be applied to all of the tasks in the DAG here as well. You define your DAG next. So that will include the schedule that you want it to run. In this example, it's running daily, which is not exactly, it is a cron expression, but we haven't gone through these special cron expressions before. Then there's a mandatory field in the DAG, and you can, which is the DAG ID, and then you can also add a description. Also, in case you have defined a set of default parameters before, like I've shown you before on a dictionary, you can pass it here. Okay. Then you define the set of tasks that will be part of your pipeline, and these often rely on some Python functions that need to be executed, or some other operators. And finally, you will define the task dependencies. So mainly if they will be executed in sequence or in parallel. The rest of the dependencies we discussed, like the trigger rules, have to be defined in the task definition or on the previous step. So now that you know what are Airflow tasks and now you can define your DAG, let's now jump to the next lesson where we will discuss more details about Airflow operators and sensors. So thank you, and I'll see you in the next video. Welcome to this lesson. We've talked previously about Airflow operators. Now let's detail what are these operators. Airflow operators are essentially blueprints for tasks. They perform actions, so they exist to help you avoiding coding everything by giving you the possibility of execute queries on let's say a database, like this operator called Postgres operator, or to execute a Python callable like this Python operator, or to load data from Google Cloud Storage to BigQuery with this GCS to BigQuery operator, for example. There are hundreds and hundreds of Airflow operators that will help you with most of your data engineering pipeline tasks. You just have to search the web for it and correctly import them into your DAG. And of course, fill the details to use them correctly. So in this example here, you can see the bash operator, which executes a bash command, and a Python operator which calls the Python function, which is called greet. So this function is previously defined on your DAG, and essentially the Python operator allows you to call it from this task inside your DAG. So let's now talk about sensors. So sensors are special operators which wait for a condition to be met before proceeding. So there are several different sensors, like the file sensor, which waits for a file to arrive, for example, in a data lake bucket. There's the time-based sensor or the external dependency sensor. These sensors are also operators, but they are special in the way that when you're using them, the main definitions that you have to have in mind is the poke interval, which is the time interval between the checks on the condition the sensor is waiting for. So meaning that let's say that you define these as 1 minute. So every 1 minute, that sensor operator will be checking the bucket on the data lake to see if the file has already arrived. Okay, and if it has arrived, it will trigger the DAG. So you can also have the timeout. So keeping with this example, so every minute it will check for the file until a specific timeout definition that you have included. For example, look for expect that the file arrives in this data lake bucket for like 10 minutes tops, and check it every minute. So then once the timeout is gone, so basically the task will fail. So this means that, and following this example, for how long will Airflow check the file has arrived until it gives up and causes the task and the DAG to fail. So the mode, it's also another definition. The mode of these checks can be poke or reschedule, which differentiate whether Airflow will do other things between the checks, or if its worker, which is the component responsible for executing the task, will simply wait there and not accepting any other work. These choices of these definitions are very important for an efficient use of resources. So here you can see an example of a sensor, which is the S3 key sensor. So basically it does what I said on the example on the previous slide. So it looks for a file in a bucket called my/bucket on the my-bucket on the AWS S3 data lake. In this case, the sensor checks every 30 seconds if the file is there or not, and does this for a total of 10 minutes. If no file is there, it will fail. And if in one of the checks the file has already arrived, it will trigger the next task called process S3 file, which is a Python operator which will probably process the file somehow. Okay, because you have to define the process file Python function and what it does and what processing does it apply to the file that has arrived. So in terms of introduction to Airflow, we've seen the main concepts, and remember, this is an introductory section about Airflow. We've talked about DAGs, tasks, sensors, operators, and task dependencies. So before jumping into the next and last lesson of this section, let's see an example of Airflow DAGs in action. So thank you, and I'll see you there.
Welcome to this lesson. In this one, we are going to see a second example on an Airflow DAG. We're actually going to dig deeper into Airflow code, the Python code that builds this Airflow DAG. It's a very simple one, but just please focus on the fact that the structure of your code will be very similar. The only difference between your pipelines will be, and this one will be, they will be more complex, of course, and the number of tasks and the task definition will also be different because of that. So here's the code that I have. This is a Visual Studio Code. It's very simple. So you import some libraries. You have to import the DAG method from Airflow, and also I'm importing the bash operator. So the bash operator is an operator that will execute bash commands. I make the definition of the DAG, so I give it an ID, which has to be unique. I give it a start date. I give it a schedule. I just tell it that I don't want the previous DAG runs to execute once I unpause the DAG. And then I define my own and only task, which is this bash operator. Task, I give it a task ID, which is mandatory. Run bash command, and then I pass the actual bash command. So what this pipeline will actually do is just to execute one task, which prints hello Airflow, and then I have the dependencies. If I would have more tasks, I would have to do something like this. So here task 3 will execute after task 2, which would be executed only after the run bash command task would happen. So this code is added to the DAGs folder in Airflow, and that's why this DAG shows up here. And now if you can see that it ran 6 times. It has a schedule of running daily, but I'm going to trigger it manually. So you can see that it is added to the queue of Airflow, so that it will be picked eventually by some worker. It was actually picked already, and it's running, and now it's ran successfully. So if I go to the last run and I go here, I can see the details on the run itself. So if I go to the logs, I can see that the output was hello Airflow, which was what was intended to be. Also, you can check the code, so if there's some differences that you have made or some updates, they will show up here. You can see that I didn't add those tasks that I was manually adding. So so here it is, the code that is just one task. I don't have to define these, but the dependency, because it's only one, there's no dependency. But if I don't define it, it will just define it in parallel with no other task, so it will run just the same. So this is a very simple example of Airflow code, and again, this one is another demo DAG. It is more complex, so there's more than one task. There's one starting task, there's then a set of dynamic tasks, and then there's the dependencies of the start task, and then a list of tasks that will be executed in parallel, and then the end task. So, but you can see that the structure will be the same. So you import your libraries, you can add some logic, you can define, you need to define your DAG, give it a DAG ID, and then you need to define your tasks with the tasks IDs to be defined as well. So I hope you enjoyed this very simple DAG, this very basic one. It's just an introductory video, so I hope you enjoyed it, and I'm sure that we're going to apply something very similar on your data engineering endeavors. So thank you, and I'll see you in the next video. Welcome to this lesson. Let's talk briefly about Airflow UI. This is a user-friendly way for you to interact with your data pipelines using Airflow. It allows you to monitor their statuses, their runs, check their tasks, and also the respective statuses of their tasks. Also, you can use some action commands to interact with tasks and DAGs. You can, for example, pause or unpause DAGs, which means that you turn one DAG to be active or inactive. And also you can trigger manually some of your DAGs. Here is an example with the pause and pause button, which activates or not the DAGs. You can check logs also and debug the things that didn't go well with your pipelines. And also you can manually define task statuses. So you can mark them, for example, as failed or as a success. Airflow UI will show you a list of DAGs that are on your Airflow instance DAGs folder. So all of your DAGs are here. You can then filter by active or paused. You can also filter by some other options. You can use tags that are associated with the DAGs also to filter, or you can search by the DAGs names. You'll also be able to see how many times did your DAGs ran, the statuses of the last run for each of their tasks. You can also check for all the history of the DAGs runs, all the history of this tasks history. You can also see the last run timestamp and when will the DAG run again. Plus you have the owner of the DAG also in this landing page, and there are mainly 3 actions that you can perform on this page. So you can trigger the DAG manually, you can pause and then pause the DAG. There are other views where you can see more details on the DAG's runs history or the graph of your DAG, and even monitor its execution in real time. So this was a brief example and lesson about Airflow UI. Let's now see a more practical approach to it. So thank you. I hope you enjoyed this video, and I'll see you in the next video. Thank you. Welcome to this lesson, which is an example and actually a tour on the Airflow UI. I know that on the intro to Airflow, one of the examples was to actually showing you the UI, but now we're going to dive a little deeper into that. So this is, again, my Airflow instance, which is running locally. We saw already this main page. You see a list of tags and some other information, but now let's actually dig into one of the DAGs. And you can see that when you choose one DAG, you'll have several options. So you can see the details on the DAG itself. So when it's going to run, if there's some parameters that you defined on the Python code or not. This is mostly the details, but you can also see the graph. For this particular DAG, we only have one task, so the graph is very simple. But if we press this second one, we'll see a different graph in which we have more tasks. You can see that 3 are in parallel, and there's a sequence of these 2 and the parallel one. So if we get back here, we can see also the Gantt. So if I press here, again, it's only one task, so you can see the time that the task took, in which status is this task been, and for how long. You can also go and check the code. So we've been through this code already. It's a relatively simple one with just one task, but you can also check the logs, which we already saw in the previous example in which we printed hello Airflow. If there's XCOMs, which are return values for each task, you can see them here as well. You can see the task duration. So there are a lot of options in which you can see more and more information about your tasks or your DAGs, and specifically if you select the task, you can elect it to clear the statuses, which mean that the task will rerun, or you can mark it as failed or successful. In this case, you can only mark it as failed because it has already succeeded well in the past. You can also see more information if you, well, I don't have more history for this, but you can look back a lot of months is even back if you keep all the metadata, and you can check and analyze exactly how often, how long will your pipeline take to run. Then also, if we get back to the main page, you have a lot of other interactions that you can do here. You can check the XCOMs. You can configure connections. You can add variables as well. So connections allow you to connect to, well, the ecosystem of data engineering. So Databricks, Snowflake, Google Cloud, AWS, a lot of databases as well. So there's probably a connector already that was built by Airflow that you'll be able to call several times and to use on your task. So there's also SLA misses that you can check. There are well, more details about the tasks. You can also we saw here variables, but they are empty. But we can add variables as well that you can use throughout your DAG. So there are a lot of interactions that you can do through Airflow UI, but mostly the DAGs will run on themselves. That's one of the goals of having an orchestrator, is to have an automation that runs the DAGs or the pipelines for yourself. But yeah, there's ways for you to trigger manually, to check the runs, to be alerted by them if you define them on the code. So yeah, so this is the basics of the Airflow UI. You saw a lot of views already. So I hope you enjoyed this lesson, and I hope that you use Airflow in the near future. So thank you, and I'll see you in the next